Hey everyone, welcome back to the channel. Before we dive into this absolutely mind-blowing and deeply unsettling exploration of what it actually means to go to Mars, make sure you hit that subscribe button and give this video a like. It really helps the channel, and trust me, what you're about to hear will completely change how you see the dream of colonizing another world. Right now, as you listen to this, there is a rock sitting on the surface of Mars that may contain the fingerprint of something that was once alive. Not a theory, not a guess. A peer-reviewed discovery published in Nature, examined by over 1,000 scientists, and no one can explain what made those patterns except biology. We may have just found proof that life existed on another world. And at the same time, we are building rockets to send human beings to that exact same planet permanently. People whose bones will dissolve in the reduced gravity, whose brains will be slowly rewritten by invisible radiation passing through their skulls every second of every day, who will watch their families grow old in recorded messages that arrive 20 minutes too late to feel real. People who may never come home, not because they chose to stay, because the fuel to bring them back does not exist yet. Tonight, we are going to tell you what it actually costs to go to Mars. Not the dream, the price. But before we begin, if you enjoy these nighttime documentaries, remember to like and subscribe. It helps us bring you more videos like this. Now let's begin. Tonight, we are going to talk about Mars, but not the way you have heard about it before. Not the inspirational version. Not the billionaire dream. Not the shiny rocket on a launch pad with a countdown clock and a crowd cheering in the Texas desert. We are going to talk about what actually happens to a human being who leaves Earth and never comes back. We are going to talk about bones that dissolve, about minds that break in silence, about radiation you cannot see or feel that rewrites the architecture of your brain while you sleep. We are going to talk about a rock on Mars that might contain the fingerprint of something that was once alive, and what it means that we are racing to land on that world before we have finished asking whether we should. We are going to talk about children who may one day be born on another planet, and who will never, for as long as they live, be able to visit the world their parents left behind. And we are going to talk about a company that has already written into its terms of service that no government on Earth has authority over what happens on Mars. This is not a story about exploration. This is a story about exile. And it begins with a delay that almost nobody noticed. On February 9, 2026, while most of America was watching the Super Bowl, Elon Musk posted something on his social media platform that should have made headlines around the world. It did not. There was no press conference, no live stream, no dramatic reveal on a stage with blue lights and a crowd of engineers applauding. Just a few sentences dropped quietly into the noise of a Sunday evening, announcing that SpaceX was shifting its focus away from Mars. The company would now prioritize building what Musk called a self-growing city on the moon. Mars, he said, would have to wait another 5 to 7 years. The overriding priority, he explained, was securing the future of civilization, and the moon was faster. Let that sit for a moment. For over 2 decades, Mars has been the mission, the reason SpaceX exists, the reason Starship was built, the reason Musk told audiences at the International Astronautical Congress back in 2016 that humans would be walking on Mars by 2024. That was the promise. That was the timeline. And every few years, when the timeline slipped, a new one replaced it. 2024 became 2026. 2026 became 2028. And now, in 2026, the target has drifted again. 5 to 7 more years, maybe, if things go well. If orbital refueling works, if the engines hold, if the math cooperates. The pattern is worth examining because it reveals something important. Not about Musk specifically, but about the gap between what Mars colonization looks like in presentations and what it looks like in physics. In 2020, Musk said he was highly confident SpaceX would land humans on Mars by 2026. In May of 2025, he said there was a 50-50th chance of sending an uncrewed Starship to Mars by late 2026. By December of 2025, he called the 2026 Mars window a distraction. And by February of 2026, the mission was officially shelved. Every version of the future arrives later than promised, and the reason is not incompetence. The reason is that Mars does not care about timelines. Mars does not care about ambition or funding or willpower. Mars is 55 million kilometers away at its closest and nearly 400 million at its farthest. The physics of getting there, surviving there, and coming back has not changed since the first engineer sketched a trajectory on a whiteboard. What has changed is our understanding of how hard it actually is. But while the world was focused on rockets and launch windows, something else happened. something quieter, something that may turn out to be more important than any rocket ever built. On September 10, 2025, NASA held a press conference. The acting NASA administrator stood at a podium and said words that scientists have been waiting decades to hear. "A rock on Mars," he said, "may contain the clearest sign of life that we have ever found." The rock is called Cheyava Falls. It sits in a place called the Bright Angel Formation along the edges of an ancient river valley called Neretva Vallis inside Jezero Crater. The Perseverance rover found it in July of 2024 and drilled a core sample from its surface. What the instruments detected was extraordinary. The rock is made of clay and silt, the kind of fine-grained sediment that on Earth is one of the best preservers of ancient microbial life. Embedded in that sediment were organic carbon compounds, sulfur, phosphorus, and iron, and scattered across the surface were strange markings. Small dark spots the science team nicknamed poppy seeds, and larger formations lighter in the center with dark borders that they called leopard spots. On Earth, those leopard spot patterns are produced almost exclusively by one thing: microbes, living organisms that consume organic matter and leave behind chemical signatures in the minerals around them. The peer-reviewed paper, published in the journal Nature, examined every known non-biological explanation for how those patterns could have formed. High-temperature processes, chemical reactions without life, geological accidents. None of them fit. The conditions required for those alternative explanations simply do not match the evidence preserved in the rock. This is not confirmation of life on Mars. Scientists are careful with that word, and they should be. But it is the most serious candidate for a biosignature ever found on another world. And the lead author of the study said something that deserves to be heard clearly. He said that the combination of chemical compounds found in the Bright Angel Formation could have been a rich source of energy for microbial metabolisms. That the organic matter in the mud had reacted with iron and sulfur to produce minerals and textures that, on Earth, are the calling card of living things. And then, just weeks earlier, in August of 2025, another study landed. This one from researchers at New York University Abu Dhabi, published in the International Journal of Astrobiology. It introduced a concept called the Radiolytic Habitable Zone. The idea is startling in its simplicity. Cosmic rays, the same high-energy particles that threaten the health of astronauts, can penetrate the surface of Mars and split apart water molecules buried underground. When those molecules break apart, they release electrons. And on Earth, there are bacteria that survive by harvesting exactly those electrons. Organisms living deep beneath the surface of our own planet, in total darkness, powered not by the sun, but by radiation. The researchers concluded that Mars may have environments just meters below the surface where this same process could sustain life right now, not billions of years ago. Now, and this is where the story splits into two paths that cannot easily coexist. On one path, humanity is preparing to send people to Mars to build habitats, to plant flags, to establish a permanent presence on a world that has been lifeless in our imagination for as long as we have been looking at it. On the other path, science is telling us that Mars may not be lifeless at all, that there may be something down there, beneath the red dust, in the frozen water, in the ancient riverbeds, something we have never encountered before, something that would change our understanding of life in the universe forever. If colonists land on Mars and contaminate the surface with Earth microbes before we have confirmed whether Martian life still exists underground, we may destroy the most important scientific discovery in human history. And we may never even know we did it. Earth bacteria are resilient. They hitchhike on everything. On suits, on boots, on the seals of airlocks, on the surfaces of tools. No sterilization protocol is perfect. No habitat is perfectly sealed. The moment a human being sets foot on Mars, Earth life arrives with them. And if Martian life is fragile, if it exists in small pockets sustained by the thin chemistry of radiolysis, it could be overwhelmed and erased by the biological invasion we bring with us. The planetary protection protocols that govern space missions today were designed for robots, for rovers and landers that can be baked in ovens and sealed in clean rooms. They were never designed for human beings who breathe and sweat and shed skin cells and carry trillions of microorganisms in every square centimeter of their bodies. There is no version of human Mars colonization that does not contaminate Mars. The question is whether that contamination happens before or after we have answered the most profound question science has ever asked. Are we alone? We are racing to colonize a world we do not yet understand. And the window to understand it may close the moment the first human steps off the landing ramp and presses a boot into Martian soil. But the journey to that moment, the actual physical act of getting a human body from Earth to Mars, is a story of distances and durations that most people have never truly reckoned with. We talk about going to Mars the way we talk about flying to another country, as though it is a matter of buying a ticket and enduring a long flight. It is not. The distance between Earth and Mars is not just large, it is a kind of large that changes the meaning of basic human experiences. Communication, emergency response, the ability to say goodbye, the ability to come home. And that distance, measured not just in kilometers but in time and fuel and orbital mechanics, is where the real story of Mars colonization begins. Because once you understand the distance, you begin to understand something that the brochures and the presentations and the inspirational videos never quite say out loud. Going to Mars is not a round trip. Not yet, and maybe not ever. Imagine you are standing in a room. On one wall there is a light switch. You flip the switch and the light comes on instantly, or at least it seems instant. In reality, the electrical signal traveled through the wire at close to the speed of light, and the delay was so small that your brain could not detect it. Now imagine the wire is longer, much longer. Imagine it stretches from your wall, out through your roof, past the atmosphere, past the moon, past everything you have ever known, all the way to Mars. You flip the switch and you wait. For minutes, 8 minutes, maybe 20, depending on where Mars is in its orbit. The signal, traveling at the fastest speed anything in the universe can travel, takes between 4 and 24 minutes just to arrive. That is the speed of light, the absolute cosmic speed limit. Nothing moves faster. Not radio waves, not laser beams, not the desperate voice of a mission controller shouting instructions into a microphone. And it means that communication with Mars is not a conversation. It is correspondence. Every message sent from Earth arrives minutes after it was spoken. Every reply takes minutes more. A simple exchange of question and answer can take 40 minutes or longer. Now imagine an emergency. A pressure seal in the habitat fails. The atmospheric alarm triggers. An astronaut has seconds, maybe a minute, to identify the breach and begin emergency procedures. They call Earth. They describe what is happening. Their voice, traveling at the speed of light, takes 14 minutes to reach mission control. The engineers on Earth hear the message, process it, formulate a response, and send it back. Another 14 minutes. 28 minutes have passed since the astronaut called for help. In 28 minutes, the astronaut is either alive because they solved the problem themselves or they are dead because they could not. Earth did not help. Earth could not help. Earth could only listen minutes too late to the sound of someone who may already be gone. This is not a hypothetical designed to frighten you. This is the operational reality of every crewed Mars mission ever proposed. The speed of light is not a technical limitation that engineers can overcome with better antennas or faster computers. It is a law of physics as immovable as gravity, and it means that the moment a spacecraft leaves the vicinity of Earth, the crew is functionally alone. They can send messages home. They can receive messages from home, but they cannot have a conversation in any meaningful sense of the word, and they absolutely cannot receive help that arrives in time to matter. The distance itself shifts constantly. Earth and Mars are both orbiting the Sun, but at different speeds and different distances. Sometimes they are relatively close. At what astronomers call opposition, Mars and Earth can be as near as 55 million kilometers apart. That is the best-case scenario, the shortest possible distance between the two worlds, and even at that closest approach, a beam of light takes over 3 minutes to cross the gap. But opposition does not last. The planets keep moving, and at their farthest separation, when the Sun sits directly between them, Mars and Earth are nearly 400 million kilometers apart. At that distance, a light signal takes over 20 minutes to arrive, and a round-trip message takes more than 40. For most of a Mars mission, the distance will be somewhere between those extremes, long enough that real-time communication is impossible. Long enough that every decision, every crisis, every moment of doubt or fear must be resolved locally by the people on Mars with whatever resources and knowledge they brought with them. But distance is only half of the trap. The other half is time. Earth and Mars do not align for efficient travel on demand. The geometry of the solar system creates narrow windows, roughly every 26 months, when the two planets are positioned favorably enough to allow a spacecraft to make the crossing with a reasonable amount of fuel. Miss that window and you do not get to try again for over 2 years. This is not a scheduling inconvenience. This is a prison sentence measured in orbital mechanics. Think about what 26 months means in human terms. It is long enough for a child to go from birth to walking and talking, long enough for a marriage to collapse, long enough for a parent to develop a terminal illness and die before the next window opens, long enough for political regimes to change, for technologies to advance, for the world the astronaut left behind to become a place they no longer fully recognize. The transit itself takes between 6 and 9 months depending on the trajectory. Add the mandatory surface time, which in most mission architectures is determined not by science goals, but by orbital mechanics because the crew has to wait for the planets to realign before they can even attempt to return. For a conjunction-class mission, that surface stay is roughly 500 days. 500 days on Mars, not because the mission requires it, but because the universe demands it. Add it all up. 6 to 9 months of transit to Mars, 500 days on the surface, 6 to 9 months of transit back. The shortest plausible round trip to Mars takes approximately 3 years. 3 years, not 3 weeks, not 3 months. 3 years of a human life spent inside sealed vessels, exposed to radiation, separated from everyone they have ever known by a communication delay that makes real human connection impossible. And that is the optimistic scenario. That is the version where everything works perfectly, where the return vehicle is fueled and functional, where the launch window is met, where no equipment fails and no crew member becomes too sick to travel. The pessimistic scenario, the one that mission planners discuss in quieter rooms, is that the return simply does not happen, that the technology required to bring people home from Mars does not work as planned, and the 3-year round trip becomes a permanent stay. But we will get to the fuel problem later. For now, consider the decision itself. There is a moment early in the journey from Earth to Mars when a spacecraft crosses a line that has no physical marker, but that changes everything. It is the point of no return, not a place in space, but a calculation. The point at which turning around and coming back to Earth requires more fuel than continuing forward to Mars. Within weeks of departure, sometimes within days, an abort becomes harder than completion. The crew is committed not by choice in any ongoing sense, but by physics. They chose to go when they boarded the spacecraft. Every moment after that, the universe is making the choice for them. Think about what that means for the psychology of the mission. Every other dangerous expedition in human history has had some version of a way back. Shackleton, trapped in Antarctic ice, could still attempt to reach land. The crew of Apollo 13, hurtling past the moon with a crippled spacecraft, had Houston talking them through every second of the crisis with a response time measured in seconds, not minutes. Submarines can surface, mountain climbers can descend, even sailors lost at sea can drift toward shore. A Mars crew has none of these options. There is no shore to drift toward. There is no surface to reach. There is only forward toward a planet that is trying to kill them in ways we have not even finished cataloging, or backward toward an Earth that is already too far away to help. The historical comparisons that people like to draw, the Mayflower, the Polynesian navigators, the first expeditions to the Antarctic, all share one crucial feature that Mars colonization does not. In every one of those cases, the environment being traversed, however dangerous, was made of the same air and water and gravity that the human body was designed for. A sailor lost in the Pacific could breathe. A settler on the American frontier could drink from a river. An Antarctic explorer could step outside and, however cold it was, the atmosphere would not boil the fluid from their lungs. Mars offers none of these mercies. The space between Earth and Mars is a vacuum that will kill you in seconds. The surface of Mars is an environment so hostile that unprotected exposure causes death within minutes. And the distance that separates the two worlds is so vast that no rescue mission currently conceivable could reach a stranded crew before their supplies ran out. This is the architecture of the journey, not a voyage, but a commitment, not an expedition, but an exile. The distance does not just separate you from Earth. It separates you from every safety net that human civilization has ever constructed. Every hospital, every fire station, every friend who could come and hold your hand, every system designed to catch you when you fall. On Mars, when you fall alone, and the people who love you find out about it 20 minutes later. The engineers designing these missions know all of this. They have calculated every trajectory, every fuel requirement, every communication delay down to the millisecond. They have built redundancy into systems and trained crews for every conceivable emergency. And still, when you ask them in private whether the return journey is guaranteed, the honest ones pause before answering. because they know that the return depends on a chain of technologies and conditions that has never been tested end to end, that the plan to come home from Mars is, at this moment, still partly theoretical. And if the return does not work, then the 26-month window becomes not a scheduling constraint, but a clock. A clock counting down to the next chance that will never come. And the distance, which was supposed to be temporary, becomes permanent. The 55 million kilometers between you and everyone you have ever loved becomes a wall that no amount of wanting can bring down. Is a plan that cannot be aborted actually a plan? Or is it a promise made to people who are not in a position to refuse? That question haunts every mission architect who has ever sketched a trajectory to Mars. And it should haunt the rest of us too, because the people who will fly that trajectory are not abstractions. They are human beings with families and memories and fears. And once they cross that invisible line, the point of no return measured not in kilometers, but in commitment, they belong to the distance. And the distance does not give anything back. But the journey is only the beginning, because even if the spacecraft arrives safely, even if the landing succeeds, even if the habitat inflates and the life support hums to life and the first human being takes a breath of recycled air on the surface of another world, there is still the question of what Mars does to the body that arrived. Not the mind, we will get to that. The body, the bones and muscles and eyes and heart that evolved over millions of years to function in one specific gravitational field on one specific planet. The human body is an extraordinary machine. It adapts, compensates, it adjusts to whatever conditions it finds itself in with a faithfulness that would be admirable if it were not, in this case, so cruel. Because the body does not know that you want to go home. It only knows where it is. And on Mars, where it is means gravity that is 38% of what it knew on Earth. And the body dutifully begins to change. It begins to become Martian. And it may never be able to change back. Start with bone because bone is where the betrayal begins. Your skeleton is not the dead scaffolding it appears to be. It is alive. It is constantly being torn down and rebuilt by two types of cells that work in opposition. Osteoclasts dissolve old bone, osteoblasts build new bone. In a healthy body under normal gravity, these two processes balance each other. Your skeleton replaces itself completely roughly every 10 years. You are, in a very real sense, not walking on the same bones you had a decade ago. But this balance depends on something your bones take for granted: gravity, mechanical loading, the constant downward pull that tells your skeleton it needs to remain strong. Every time you stand up, every time you walk across a room, every time you climb a flight of stairs, your bones receive the signal that says yes, keep building. Stay dense. Stay hard. You are needed. In microgravity, that signal disappears. The osteoclasts keep working. They dissolve bone on schedule because that is what they do, but the osteoblasts slow down because the mechanical signals that drive their activity are gone. The result is a net loss. Bone density drops by 1 to 2% per month in the weight-bearing regions of the skeleton. The hips, the spine, the legs, the parts of you that exist specifically to hold you upright in a gravitational field. A 6-month transit to Mars spent in the microgravity of a spacecraft produces a bone density loss of 6 to 12%. That is before you even arrive. That is just the price of the journey. And then you land on Mars where gravity is 38% of what your body evolved for. Is that enough to stop the loss? Nobody knows. We have never tested it. The International Space Station operates at near zero gravity, and everything we know about bone loss in space comes from that environment. We have no data on what happens to human bones at 0.38 g over months or years. We are guessing. The best guess based on animal studies and modeling is that Martian gravity may slow the decline but not stop it. Now add the return transit. Another 6 to 9 months in microgravity. By the time a Mars astronaut arrives back on Earth, assuming they come back at all, they may have lost 20 to 30% of their bone density in the weight-bearing regions of their skeleton. To put that in perspective, a postmenopausal woman with osteoporosis has lost roughly 30% of her peak bone density. A returning Mars astronaut could arrive home with the skeleton of an elderly person, regardless of their actual age. And here is the part that the recovery studies do not advertise loudly enough. Bone loss in space is not fully reversible. NASA astronaut Scott Kelly spent 340 days aboard the International Space Station, the longest continuous stay by an American. After his return, studies showed that while some bone density recovered, the microarchitecture of his bones, the internal structure that gives bone its strength, had been permanently altered. The bone came back, sort of, but it came back different, weaker, more brittle, less capable of withstanding the forces that daily life on Earth demands. Scott Kelly spent less than a year in space. A Mars round trip takes 3. We have no data for what happens at that scale. We are sending people into an experiment that has never been run, using their own bodies as the test subjects. But bone is only the beginning. The skeleton is just the most measurable casualty of a body under siege. The eyes are next. In 2011, NASA identified a condition that would come to be called Spaceflight-Associated Neuroocular Syndrome, or SANS. Roughly 2/3 of long-duration astronauts experience some degree of visual impairment. The mechanism is fluid shift. On Earth, gravity pulls blood and cerebrospinal fluid downward, toward your feet. In microgravity, that fluid redistributes toward your head. The increased intracranial pressure pushes against the back of the eye, distorting the optic nerve, flattening the eyeball, causing changes in vision that range from mild blurriness to significant impairment. Some of these changes reverse when the astronaut returns to Earth. Some do not. Several astronauts have reported permanent changes to their vision after long-duration missions. They came home seeing differently than when they left, not because of an injury, not because of a disease, because their own body, adapting faithfully to the conditions it found itself in, reshaped the organs they see through. Now, consider the heart. Your heart is a muscle. Like all muscles, it responds to demand. In Earth gravity, your heart works constantly to pump blood upward against gravity, to your brain, to your arms, to every part of you that sits above your center of mass. In microgravity, that work is no longer necessary. Blood flows freely without the need for the heart to pump against a gravitational gradient. And so, the heart does what any muscle does when its workload decreases. It atrophies. It gets smaller. It gets weaker. When an astronaut returns to Earth after a long-duration mission, their heart must suddenly resume pumping against full gravity with a muscle that has been downsized for the job. The result is orthostatic intolerance, the inability to stand without fainting. Blood pools in the legs. The weakened heart cannot push it back up to the brain fast enough. The astronaut stands, feels dizzy, and collapses. This happens to almost every astronaut who returns from long stays in space. It is documented, expected, and planned for. Medical teams are waiting when they land. On Mars, there will be no medical team waiting. The crew arrives after 6 to 9 months in microgravity and must immediately begin functioning in a gravitational field. Reduced gravity, yes, but gravity nonetheless. If their hearts have atrophied during the transit, if their cardiovascular systems have remodeled for 0G, the simple act of standing up and walking across the surface of Mars could be a medical event. And then there is the spine. In microgravity, without the compressive force of gravity, the intervertebral discs expand. Astronauts gain 1 to 2 inches in height during space missions. This sounds harmless. It is not. The expanded discs are more vulnerable to herniation. Back pain is nearly universal among returning astronauts. And herniated discs, which can cause severe pain, numbness, and loss of mobility, are documented at elevated rates in the years following spaceflight. Each of these systems, bone, eyes, heart, spine, fails in its own way, but together, they create something worse than any individual degradation. Cascade, a body that has adapted faithfully and irreversibly to a place that is not home. A body that has become optimized for reduced gravity, for fluid distributions that do not exist on Earth, for a cardiovascular workload that Earth does not offer. The cruelty is in the faithfulness. Your body does not resist the changes. It embraces them. It is trying to help you survive where you are. It does not know that you want to go back. And this brings us to a question that no one can yet answer, but that should keep every mission planner awake at night. If a colony on Mars survives long enough, if the habitats hold and the life support functions and the food production works and the radiation does not kill everyone first, then eventually there will be children born on Mars. Not astronauts who chose to go, not volunteers who signed consent forms, children, human beings who had no say in the matter. A child born on Mars will develop in 38% gravity from the moment of conception. Their bones will form under a gravitational load that is less than half of what human skeletons evolved to support. Their muscles will calibrate to Martian conditions. Their cardiovascular system will develop for a world where pumping blood is easier, where the heart does not need to be as strong, where the entire architecture of the circulatory system can afford to be smaller, thinner, less robust. Animal studies in simulated partial gravity suggest that developing organisms in sub-Earth gravity produce skeletons and musculature insufficient for terrestrial conditions. Bones that formed under reduced gravity lack the density and microstructure needed to withstand normal Earth gravity. Muscles that developed without full gravitational loading cannot generate the force required to move a body that suddenly weighs 2.5 times what it has ever weighed before. A child born and raised on Mars may be biologically incapable of ever visiting Earth. Not because of a travel restriction, not because of politics or cost, because their body, the body that Mars built, would collapse under the weight of the world their parents came from. Their bones might fracture. Their heart might fail. Their spine, calibrated for a gentler gravity, might compress in ways that cause permanent damage. We have never run this experiment with humans. We have no data. We have models, extrapolations, educated guesses, but we do not know with certainty what happens when a human being develops from embryo to adult in 38% gravity. What we do know is that gravity shapes everything about how a body is built. And if that gravity is wrong, if it is too little, the body that results will be calibrated for a world that is not Earth. The first generation born on Mars would not be colonists. They would be exiles, trapped not by choice, but by biology on a world they did not choose, unable to visit the planet that every story and every screen and every voice from Earth tells them is home. Home for them would be a concept, a word attached to a pale blue dot in the sky that they can see but never touch.
Terre parent chose Mars.
The children inherited it. And the distance between those two experiences, the distance between choosing exile and being born into it, may be the most profound ethical question that Mars colonization forces us to confront. But the body does not only have to contend with gravity. There is something else in the journey between Earth and Mars and on the Martian surface itself that is invisible, silent, and relentless. Something that passes through the walls of spacecraft and the fabric of spacesuits and the tissue of the human body without slowing down. Something that rewrites DNA, disrupts neural connections, and increases the probability of cancer with every second of exposure. It is radiation, and it is, in many ways, the most terrifying threat of all because you cannot see it. You cannot feel it. You cannot run from it. And on the way to Mars and on the surface of Mars, there is nowhere to hide. On Earth, you are protected by two shields that you have probably never thought about. The first is the magnetosphere, an invisible bubble of magnetic force generated by the churning iron core deep beneath your feet. It deflects most of the charged particles streaming through space, bending them away from the planet like water around a stone in a river. The second is the atmosphere, a thick blanket of gas roughly 100 kilometers deep that absorbs and scatters whatever radiation the magnetosphere lets through. Together, these two shields reduce your annual radiation exposure to roughly 2 to 3 millisieverts, a dose so low that your body repairs the damage almost as fast as it accumulates. On Mars, both shields are gone. Mars lost its global magnetic field billions of years ago when its iron core cooled and solidified. Without that magnetic dynamo, there is nothing to deflect the charged particles that fill interplanetary space. And the Martian atmosphere, what remains of it, is less than 1% of Earth's atmospheric pressure, too thin to block cosmic radiation, too thin to stop the high-energy particles that have been traveling through the galaxy for millions of years at nearly the speed of light. The radiation environment between Earth and Mars and on the Martian surface consists of two distinct threats. Understanding both of them is essential to understanding what a Mars mission actually does to the people inside it. The first threat is solar particle events. These are bursts of radiation ejected by the sun during solar flares and coronal mass ejections. They are violent, intense, and somewhat predictable. When a major solar event occurs, a storm of protons and electrons races outward through the solar system at speeds approaching a significant fraction of the speed of light. If a spacecraft or a surface crew is caught in the path of one of these storms without adequate shielding, the radiation dose can be severe. High enough to cause acute radiation sickness. High enough, in extreme cases, to be fatal. The good news, if you can call it that, is that solar particle events can be partially shielded against. The protons they contain are relatively low in energy compared to the other type of space radiation, and a few centimeters of water, polyethylene, or even regolith piled over a habitat can reduce the dose substantially. The bad news is that you need warning. You need time to get inside a shielded area, and on the surface of Mars, with no magnetic field and almost no atmosphere, the warning time for a solar particle event could be as little as 15 minutes. The second threat is far worse, and it is the one that keeps radiation biologists awake at night: galactic cosmic rays. These are not particles from the sun. They are the remnants of supernovae, the explosions of dying stars that occurred millions or even billions of years ago in other parts of the galaxy. The nuclei of atoms, stripped of their electrons, accelerated to nearly the speed of light by the unimaginable forces of stellar death. They have been traveling through the cosmos for eons, and they carry energy so high that no practical amount of shielding can stop them. This is the part that defies intuition. You might think that thicker walls would solve the problem. More metal, more protection, more stuff between you and the radiation. But galactic cosmic rays do not behave like ordinary radiation. When a high-energy cosmic ray nucleus strikes a sheet of aluminum, it does not simply stop. It shatters. It breaks apart into a spray of secondary particles, neutrons, protons, pions, gamma rays, that scatter in all directions. These secondary particles can actually deliver more biological damage than the original cosmic ray would have on its own. This is called the secondary particle cascade, and it means that thin shielding can make the radiation problem worse, not better. Adding a few centimeters of aluminum to a spacecraft hull can increase the total biological dose the crew receives because the secondary particles generated by the shielding are more damaging to human tissue than the primary cosmic rays passing through. The Curiosity rover carried a radiation detector called RAD during its transit to Mars in 2011 and 2012. It measured an average dose rate of roughly 1.8 millisieverts per day in deep space. Let that number settle. On Earth, you receive 2 to 3 millisieverts per year. In deep space, you receive that amount every day and a half. A 6-month transit to Mars accumulates approximately 300 millisieverts. The surface of Mars, with its thin atmosphere providing minimal shielding, adds another 0.67 millisieverts per day. A 500-day surface stay adds roughly 335 millisieverts more. Add the return transit, and a complete round trip to Mars exposes the crew to somewhere between 600 and 1,000 millisieverts of radiation. For context, NASA sets career exposure limits for astronauts that are designed to keep their excess lifetime cancer risk below 3%. A Mars round trip approaches or exceeds those limits, and NASA's own peer-reviewed studies have estimated that the radiation-induced mortality risk for a Mars mission crew could exceed 5%, with upper bounds approaching 10%. 10%. 1 in 10. That is not a risk statistic for an experimental program. That is a mortality rate that would shut down any commercial airline, any hospital, any industrial operation on Earth. And it accounts only for cancer. It does not include the other thing that radiation does, the thing that may be more frightening than cancer because it is more immediate and harder to detect. It damages the brain. Researchers at the University of California, Irvine, have conducted some of the most detailed studies ever performed on the effects of cosmic ray analogs on the mammalian nervous system. The experiments used particle accelerators to simulate the type of radiation astronauts would encounter in deep space, exposing mice to low doses of heavy ion radiation over extended periods. The results were deeply unsettling. The irradiated mice showed persistent impairments in hippocampal function, the brain region responsible for forming new memories and for spatial navigation. They showed deficits in cortical reasoning, the higher-order thinking that governs problem-solving and decision-making. They showed reduced ability to extinguish conditioned fear responses, meaning they remained anxious and reactive to stimuli long after the stimuli had stopped being relevant. Their dendritic complexity, the branching structures of neurons that form the physical basis of thought and memory, was measurably reduced. The connections between neurons were degraded. In some cases, they appeared to be broken entirely. And these changes were not temporary. They persisted for months after irradiation. In a mouse, months represents a significant fraction of its lifespan. Scaled to a human Mars mission, the equivalent exposure would last not months, but years. The researchers estimated that in a crew of 5 astronauts traveling to Mars and back, at least one member would be expected to display severe cognitive deficits by the time they return to Earth. At least one. That is not a fringe prediction from an alarmist study. That is a calculation published by NASA-funded radiation biologists based on the best animal data available. Picture what this means operationally. A crew member 18 months into a Mars mission, living inside a sealed habitat on a world where every decision could be the difference between survival and death, is making those decisions with a brain that has been physically altered by invisible particles passing through their skull every second of every day. Their memory may be impaired. Their reasoning may be slower. Their ability to manage stress and fear may be compromised. and they may not notice the decline. That is perhaps the cruelest part. Cognitive degradation is not like a broken arm. You do not feel it happen. You do not look down and see the damage. You simply become slightly less capable, slightly less sharp, slightly less yourself, and you have no way of knowing how much you have lost. The emergency that requires the fastest thinking finds the brain least capable of providing it. And then there are the children. If a colony establishes itself on Mars, if human beings reproduce there, the children born on that world will begin accumulating radiation exposure from the moment they are conceived. Not as adults whose bodies have finished developing. Not as astronauts who accepted the risk with full knowledge. As embryos, as infants, as growing children whose cells are dividing faster and more chaotically than at any other period of their lives. Developing organisms are far more vulnerable to ionizing radiation than adults. A cell that is dividing is a cell whose DNA is unwound, exposed, and vulnerable. A mutation introduced during embryonic development can cascade through trillions of subsequent cell divisions, affecting every tissue the mutated cell contributes to. The radiation doses on the Martian surface, accumulated over a childhood, would be unlike anything ever experienced by a developing human being in the history of our species. We have ethical frameworks on Earth that prohibit exposing children to these kinds of risks, institutional review boards, informed consent requirements, protections for vulnerable populations. None of these frameworks currently extend to children born on another planet. There is no regulation, no treaty, no law that addresses the question of what radiation exposure is acceptable for a child who was conceived on Mars and has no option to leave. Who consented for those children? Who bears responsibility for what the radiation does to their developing brains, their growing bones, their dividing cells? The parents who chose to colonize Mars? The company that transported them? The governments that funded the mission? The engineers who designed the habitats? At what point does the desire to build a new civilization become an act of harm against the people who will be born into it? That question has no answer yet, but it hangs over every Mars colonization plan ever drafted because every plan that includes long-term habitation implicitly includes the possibility of children. And every child born on Mars will live their entire life inside a radiation environment that we would never willingly expose a child to on Earth. The invisible killer does not discriminate. It does not care about ambition or courage or the dream of a multiplanetary species. It passes through walls and skin and bone with equal indifference. And on the surface of Mars, under a sky that offers no protection and no mercy, it will be there every second of every day doing its quiet, patient work. But radiation is not the only way Mars tries to kill you. The planet itself, its atmosphere, its soil, its weather, is a machine designed for death. And understanding what the surface of Mars actually is, not the way it looks in photographs, but the way it would feel against your skin and inside your lungs, is essential to understanding why going there is not exploration. It is survival every second, without pause, for as long as you live. Mars has an atmosphere. This is important to understand because when people hear the word atmosphere, they picture something like Earth's. A breathable blanket of air, dense and warm, holding in heat and keeping out the void. Mars has nothing like that. What Mars has is a ghost of an atmosphere, a thin whisper of gas pressing down on the surface at roughly 6 millibars. For comparison, the atmospheric pressure at sea level on Earth is 1,013 millibars. The Martian atmosphere is less than 1% of that. This is not just thin. This is functionally a vacuum. If you were to step outside a Mars habitat without a pressure suit, the air inside your lungs would expand violently. The moisture on your tongue and in your eyes would begin to boil, not because of heat, but because of the lack of pressure. At 6 millibars, the boiling point of water drops below human body temperature. Your blood would not boil immediately. Your circulatory system maintains its own internal pressure, but the exposed fluids of your body, your saliva, the tears coating your eyes, the moisture lining your airways, would vaporize. You would not freeze first. The common image of a person stepping onto Mars and turning into an ice sculpture is wrong. You would suffocate. Carbon dioxide, which makes up 96% of the Martian atmosphere, would flood into your lungs with every reflexive gasp. And at concentrations that high, unconsciousness comes within seconds. Death follows within minutes. The temperature adds its own dimension of hostility. The average surface temperature on Mars is minus 60 degrees Celsius. At the equator on a summer afternoon, it can climb to a relatively mild 20 degrees. But at night, At the poles or during winter, temperatures plunge to -140 degrees or below. That is cold enough to freeze carbon dioxide directly out of the atmosphere. Cold enough that the dry ice forming on the Martian surface is not water ice, but frozen gas. A human being exposed to these temperatures without protection would experience rapid core temperature decline. Hypothermia would set in within minutes. Frostbite on exposed skin would begin almost immediately. But again, you would not die of cold. You would die of the atmosphere or the lack of it long before the temperature killed you. The photographs of Mars are beautiful. They really are. The russet dunes, the layered canyon walls of Valles Marineris, the soft pink sky at sunset. There is a haunting majesty to the Martian landscape that speaks to something deep in the human imagination. But every one of those photographs was taken by a machine that does not need to breathe. A machine that does not have lungs or blood or skin. The beauty of Mars is the beauty of a place that will kill you the moment your technology fails. And then there is the dust. Mars is a dusty world. Wind storms lift fine particles from the surface and carry them across the planet, sometimes growing into global events that shroud the entire world in a haze that can last for months. The dust itself is remarkably fine, with particles measured in micrometers, far smaller than grains of sand, closer in size to the particles in cigarette smoke. And it is everywhere. It coats every surface. It infiltrates every seal. It works its way into machinery, into joints, into the mechanisms of solar panels and the threads of screws. In 2018, a global dust storm on Mars killed the Opportunity rover. Opportunity had operated for over 14 years, far exceeding its 90-day design life, surviving everything Mars could throw at it until the dust came. The storm reduced sunlight reaching the solar panels to near zero for weeks. Without power, the rover's heaters could not function. Without heat, the electronics froze. After 14 years of faithful operation, Opportunity's last transmission was a poetic final data point. Its battery was dying, the sun was disappearing, and there was nothing anyone could do. For a human colony dependent on solar power, a global dust storm is an existential threat. Energy generation drops below the threshold for life support. Oxygen production slows. Heating systems falter. And the storm does not care about your timeline or your reserves. Can last 100 days. Can last longer. And while it rages, you sit inside your habitat watching the power gauge decline, rationing every watt, wondering whether the sun will come back before the batteries die. But the most insidious danger in the Martian dust is not what it does to machines. It is what it does to lungs. In 2008, NASA's Phoenix lander confirmed something that changed the calculus of Mars surface operations forever. The Martian soil contains perchlorates, reactive chlorine compounds that are toxic to the human thyroid gland. Subsequent missions confirmed that perchlorates are not localized. They are spread across the entire Martian surface at concentrations that would classify any comparable site on Earth as a hazardous waste area. Perchlorates are colorless, odorless. You cannot see them on the dust that coats your gloves when you come back inside. You cannot smell them on the particles that settle on the surfaces of your habitat. They enter through every pathway available. On the soles of boots, on the fabric of suits, on equipment brought inside for maintenance. They contaminate food production systems. They accumulate in air filtration units. And they do their damage slowly, disrupting thyroid function, interfering with iodine uptake, potentially leading to hypothyroidism and developmental problems over time. And perchlorates are not the only hazard in the dust. Martian soil also contains fine silicate particles that some researchers have compared to the properties of asbestos. These particles, when inhaled, can embed themselves deep in lung tissue, triggering inflammatory responses that may lead to scarring, fibrosis, and eventually cancer. Studies have warned that prolonged inhalation of Martian dust could produce lung conditions similar to those suffered by asbestos workers on Earth, a group whose disease rates are well documented and deeply troubling. The colonist who survives radiation, who survives the transit, who survives the cold and the vacuum and the isolation, may still develop cancer from the dust they could not help breathing. Because you cannot keep dust out of a habitat on Mars, not perfectly, not forever. Airlocks are designed to minimize contamination, but every time a door opens, every time a suit is removed, every time equipment is brought inside, some dust comes with it. Over months and years, that accumulation adds up. And the particles do not leave your lungs once they arrive. Apollo astronauts on the Moon experienced something similar. Lunar dust, tracked into the command module after moonwalks, irritated eyes and airways. Harrison Schmitt, the geologist astronaut of Apollo 17, described symptoms resembling hay fever after exposure to lunar dust in the cabin. And the Apollo missions lasted only a few days. Mars colonists would be breathing trace amounts of Martian dust for years. For lifetimes, the planet is not just inhospitable. It is actively working against you at every scale, from the global dust storms that can darken the sky for months to the microscopic particles that lodge in the tissue of your lungs. The atmosphere will suffocate you. The temperature will freeze you. The soil will poison you. And there is nowhere on the entire surface of Mars, not a single square meter, where a human being can stand unprotected and survive. Every second of human life on Mars will depend on technology, on seals that do not fail, on power systems that do not die, on filtration that does not clog, on suits that do not tear, on 1,000 systems working perfectly simultaneously, without interruption, for years on end. There is no margin for error on Mars because there is no backup. On Earth, if your house loses power, you go to a neighbor. If your car breaks down, you call someone. If the air quality is bad, you go indoors. On Mars, indoors is the only place you can be. And if indoors fails, outside is not an alternative. Outside is death. The engineers designing Mars habitats understand this. They design for redundancy. They build in backup systems and emergency protocols and fail-safe mechanisms. But they also understand something that they rarely say out loud. No system is perfectly reliable over infinite time. Everything fails eventually. Seals degrade. Filters saturate. Electronics corrode. And on a planet where a single catastrophic failure can kill everyone in the habitat, the question is not whether something will go wrong. The question is when, and whether anyone will be alive to fix it. Mars is not a frontier waiting to be settled. It is an environment that has been lifeless on its surface for billions of years for very good reasons, and every one of those reasons applies equally to the human beings who propose to live there. But if the planet attacks the body, what does it do to the mind? What happens to a human being who knows with absolute certainty that they are trapped on a hostile world, that the people they love are 20 minutes away by light speed, that the door they came through may never open again to let them go home? The answer is something that no simulation has fully captured, and no training can fully prepare anyone for. Because the psychology of permanent exile is not an engineering problem. It is a human one, and the human mind, for all its resilience, has limits that Mars will test in ways we have barely begun to understand. There is a moment in every long isolation that researchers call the third quarter phenomenon. It occurs roughly 3/4 of the way through a confined mission, when the end is close enough to feel, but far enough away to crush morale. In Antarctic winter-over stations, the third quarter brings spikes in depression, hostility, and sleep disturbance. In submarine crews, it brings irritability and withdrawal. In space station missions, it brings a measurable decline in communication with mission control as crews begin to pull inward, to stop reporting their emotional states, to manage their suffering in silence. On a Mars mission, the third quarter does not arrive and pass. On a one-way mission, it never ends. The psychological profile of Mars isolation has no true analog in human experience. We can compare it to other forms of confinement, and researchers have tried, but every comparison eventually breaks down because every comparison has an escape valve that Mars does not. Astronauts on the International Space Station are isolated, yes, but they can see Earth through the window. A blue sphere that fills the sky, close enough to feel tangible, real, within reach. They can video call their families with delays measured in seconds. They know that if something goes genuinely wrong, if a medical emergency occurs that the crew cannot handle, a Soyuz capsule can return them to Earth within hours. The psychological safety net is enormous. The isolation is real, but it is bounded. It has walls. It has an end date. Antarctic winter-over crews at the South Pole endure months of darkness, extreme cold, and near-total isolation from the rest of humanity. The nearest help during the winter months is thousands of kilometers away and may not be able to reach them. Depression rates during Antarctic winter are high. Interpersonal conflicts are common. Sleep disorders are nearly universal. And yet, even the most isolated Antarctic crew knows two things. They know it will end, and they know that in the most extreme emergency, an evacuation flight could be attempted, risky, dangerous, but possible. Mars colonists have neither of these comforts. They cannot see Earth in any meaningful way. It is a point of light in the sky indistinguishable from a star. They cannot call home and expect a response in real time. Their messages arrive on Earth minutes after they are sent, and the replies take minutes more to come back. A conversation becomes an exchange of monologues separated by silences so long that the emotional thread of the interaction breaks. Think about what that does to a relationship. Any relationship, a spouse, a parent, a best friend. Relationships are maintained through spontaneity, through the small, unplanned moments that give human connection its texture. The unexpected call, the shared laugh at something that just happened, the ability to say, "I love you," and hear "I love you, too," in the same breath. On Mars, none of that is possible. You record a message. You send it into the void. You wait 20 minutes. You receive a response that was recorded 20 minutes ago to something you said 40 minutes ago. The conversation is always out of sync. The emotional moment has always passed by the time the response arrives. Over time, the spontaneity dies. Then the intimacy follows. Then the sense of shared time. And eventually, a relationship that was once the center of your emotional life becomes a kind of literary exchange. Letters sent into space. Beautiful, perhaps. Heartfelt, perhaps. But no longer a living connection. Just a record of what was. Children grow up. You watch it in recorded videos that arrive weeks after the moments they captured. A first step, a first word, a first day of school. You see these milestones with a delay that makes them feel like memories before you have even experienced them. Your child is already beyond the moment by the time you learn it happened, and you cannot participate. You cannot cheer. You cannot hold them up. You are a spectator to your own family's life, watching from a distance that no technology can close. In 2010, the Russian Institute for Biomedical Problems conducted an experiment called Mars 500. 6 volunteers entered a sealed facility in Moscow and remained there for 520 days, simulating the duration of a Mars round trip. They had communication delays built into their interactions with the outside world. They had confinement, limited resources, and the monotony of a closed environment. The results were sobering even in that controlled setting. Crew members experienced significant sleep disruption. 2 of the 6 volunteers developed symptoms consistent with depression. Interpersonal dynamics deteriorated over time, with increasing withdrawal and reduced communication between crew members and simulated mission control. The researchers identified a phenomenon they called autonomization, a progressive disengagement from external support structures that mirrors what happens in real long-duration space missions. And these subjects knew they were on Earth. They knew that beyond the sealed doors of their habitat, Moscow continued to exist. They knew that if a genuine medical emergency occurred, help was literally on the other side of the wall. They knew it would end. Real Mars colonists know none of these things. Every psychological stressor identified in Mars 500 would be amplified by the knowledge that the isolation is real, that the door does not open onto a Russian research facility, but onto a world that will kill you in 90 seconds, and that there is no end date. But there is one dimension of Mars psychology that no simulation has ever tested. One form of suffering that is unique to the condition of permanent exile at interplanetary distance. And it may be the heaviest burden of all: grief. Every Mars colonist will eventually learn that someone they loved has died on Earth. A parent, a sibling, a friend. Someone they held once in a gravity that their body can barely remember. And they will learn this fact not through a phone call, not through a knock on the door, not through the embrace of someone who shares their sorrow. They will learn it from a message. A recorded message that traveled at the speed of light across millions of kilometers and arrived in their inbox hours after the death occurred. They will sit inside a sealed habitat on an alien world and read or hear the words that tell them someone is gone. And they will grieve alone. There will be no funeral to attend, no gathering of people who share the loss, no ritual, no ceremony, no communal expression of sorrow. Human beings have developed rituals for grief over thousands of years because grief shared is grief that can be survived. The wake, the memorial, the act of gathering with others who knew the person who died and saying together, "This mattered. This person mattered." On Mars, none of that exists. The colonist grieves in a room that smells of recycled air, surrounded by people who have their own losses and their own burdens, on a world that offers no comfort and no release. And the grief does not come once. It comes repeatedly because everyone the colonist left behind on Earth will continue to age, to change, to eventually die. And the colonist will watch it happen slowly, across years of recorded messages, watching the people they loved grow older in a time delay that makes every conversation feel like speaking to a ghost. The anticipation may be worse than the event. The colonist who watches their parent age through recorded videos, who notices the slower movements and the grayer hair and the more careful speech, knows what is coming. They can see the trajectory, and they know that one day the message will arrive that says it happened. And they will be the last to find out and the only one who cannot come to say goodbye. Can a person remain fully human while grieving alone for years, with no community of shared mourning, no ritual, and no hope of return? That is not a rhetorical question. It is a clinical one. And the answer is that we do not know, because no human being has ever been placed in that condition. We have data on grief in isolation. We have data on grief at a distance. We have data on grief without ritual. But we have no data on all three simultaneously, sustained over years with no possibility of relief. The psychology of Mars colonization is not an afterthought. It is not a soft problem to be solved with better crew selection, or more exercise equipment, or monthly sessions with a therapist on a 20-minute delay. It is a core engineering constraint, as fundamental as fuel and oxygen and radiation shielding. Because a crew that is physically healthy, but psychologically broken, is a crew that cannot function. And a crew that cannot function on a world that punishes every mistake with death is a crew that will not survive. The mind that goes to Mars will be tested in ways that no mind has been tested before, and the question that sits at the center of every psychological study ever conducted on long-duration spaceflight is not whether the mind will break. It is what happens when it does. Because on Mars, there is no evacuation. There is no medical leave. There is no stepping outside for fresh air. There is only the habitat, the red dust beyond the window, and the pale blue in the sky that gets a little harder to find with each passing year. And even if the mind holds, even if the body adapts, even if the habitat functions and the crew survives, there is still the question that makes every other question moot. The question of whether they can come home at all, because the technology required to bring a human being back from Mars does not currently exist, and the mathematics of why it does not exist are as unforgiving as the radiation and the distance and the dust. There is a law in rocketry that governs everything. It is called the Tsiolkovsky rocket equation, and it was first derived by a Russian schoolteacher in 1897. The equation itself is simple. The implications are brutal. Here is the core problem stripped of all jargon. To move a spacecraft, you need fuel. Fuel has mass. To carry that mass, you need more fuel. And to carry the fuel that carries the fuel, you need even more fuel. The relationship is not linear. It is exponential. Every additional kilogram of payload you want to deliver to Mars requires not just one additional kilogram of fuel, but many additional kilograms, because each kilogram of fuel added must itself be lifted, which requires its own fuel, which requires its own fuel, and so on. This is sometimes called the tyranny of the rocket equation, and it is not a metaphor. It is a mathematical wall that has defined the limits of space travel since the first rocket left the ground. For getting to Mars, the tyranny is manageable, barely. A spacecraft can carry enough fuel to make the outbound journey because it does not need to carry the fuel for the return. The mass budget can be spent on payload, on life support, on the 1,000 things a crew needs to survive. But the moment you add a return trip to the equation, the mathematics become catastrophic. To return from Mars, a spacecraft needs fuel. That fuel must be on Mars when the crew is ready to leave. Can get there in one of two ways. Can be carried from Earth, or it can be manufactured on Mars. There is no third option. Carrying return fuel from Earth is essentially impossible with current or near-future technology. The gear ratio is staggering. For every kilogram of propellant you want to deliver to the Martian surface, you must launch approximately 226 kilograms from Earth. That is not a typo. 226 to 1. That ratio accounts for the fuel needed to lift the fuel from Earth's gravity well, to accelerate it to interplanetary speed, to decelerate it at Mars, and to land it safely on the surface. A SpaceX Starship returning from Mars would need somewhere between 33 and 100 tons of methane and liquid oxygen propellant. At a 226 to 1 ratio, delivering even the minimum amount would require launching over 7,000 tons from Earth. For comparison, the Saturn V, the most powerful rocket ever successfully flown before Starship, had a total launch mass of roughly 3,000 tons. You would need the equivalent of more than 2 full Saturn V launches just to deliver enough return fuel for one Starship. The numbers do not work. They have never worked, and they are why every serious Mars mission architecture since the 1990s has relied on the same alternative. Make the fuel on Mars. In-situ resource utilization, or ISRU, is the name for this idea. The chemistry behind it is real and well understood. The Sabatier reaction combines carbon dioxide with hydrogen to produce methane and water. Electrolysis splits water into hydrogen and oxygen. Mars has abundant carbon dioxide in its atmosphere and water ice beneath its surface. In principle, a chemical plant on Mars could extract these resources, process them, and produce the methane and liquid oxygen that a starship needs to fly home. NASA even demonstrated a proof of concept. The MOXIE experiment aboard the Perseverance rover successfully extracted oxygen from the Martian atmosphere. It worked. It produced roughly 12 grams of oxygen per hour. That is about as much oxygen as a small tree produces in the same time. 12 grams per hour. A starship needs tens of tons of liquid oxygen to return to Earth. The gap between 12 grams per hour and the 33 to 100 tons required is not a gap. It is an abyss. Scaling from a laboratory demonstration to industrial production requires building, transporting, landing, deploying, and operating a chemical processing facility on the surface of another planet. A facility that must run autonomously for months or years before any crew arrives. A facility that must function in temperatures that drop below -100 degrees Celsius. A facility that must process Martian regolith or atmospheric gases in an environment filled with the corrosive perchlorate dust we discussed earlier. No such facility has ever been built. None has been tested on Mars. None has been operated in Martian conditions for the multi-year duration required to accumulate sufficient propellant. We have the chemistry. We do not have the engineering. And the distance between having the chemistry and having a working factory on Mars is the same kind of distance that separates a blueprint from a building. But suppose the ISRU plant is built and it works. Suppose it produces enough methane and liquid oxygen over the course of 2 years to fill a starship's tanks. There is still the storage problem. Methane and liquid oxygen are cryogenic fuels. They must be kept extremely cold to remain liquid. On Earth, this is managed through insulated tanks and active refrigeration systems. On Mars, in a thin atmosphere with wild temperature swings, keeping cryogenic fuels from boiling off over months or years is an unsolved engineering challenge. When cryogenic fuel warms up, it transitions from liquid to gas. The pressure inside the tank increases. If the tank cannot contain the pressure, the fuel must be vented or the tank ruptures. Either way, you lose fuel. This is called boil-off, and it is not a minor concern. It is a fundamental constraint on long-duration storage of cryogenic propellants. Engineers have noted that no valves currently exist with truly zero leakage. Even tiny, imperceptible leaks compound over months and years. A 2-year wait for a return launch window means even minuscule losses matter enormously. SpaceX's architecture requires orbital refueling of Starship before departure from Earth, a capability the company has yet to demonstrate. But the Mars return requires something harder. It requires fuel produced on another planet, stored for years without significant loss, and loaded into a vehicle that has been sitting on the Martian surface exposed to temperature extremes, dust, and radiation for the duration of the surface stay. Now walk through the full return sequence. Every step must work. The ISRU plant must be deployed and functional. Propellant must be produced in sufficient quantities. That propellant must be stored without catastrophic boil-off for months or years. An ascent vehicle, the Starship itself, must be capable of igniting its engines after years of dormancy on Mars. There is no test firing possible. The first time those engines light will be the time they must work. If they do not ignite, the crew is stranded. Assuming liftoff succeeds, the vehicle must achieve Mars orbit. It must execute a trans-Earth injection burn at precisely the right moment. It must survive a 6 to 9 month return transit, and it must re-enter Earth's atmosphere and land safely. Each step in that chain has a probability of success. Let us be generous and assign 90% reliability to each one. That is a high number for systems that have never been tested in these conditions. 90% sounds good, but chain 7 or 8 90% probabilities together, and the overall probability of complete mission success drops to roughly 50%. Flip a coin. That is the reliability of a Mars return using technology that does not yet exist, operated in conditions that have never been tested, with the lives of the crew depending on every link in the chain holding. A 2024 analysis examined the feasibility of SpaceX's Mars mission architecture and arrived at a conclusion that deserves to be quoted carefully. The authors wrote that reliance on ISRU technology for the return flight mandates significant reliability to avoid stranding crew on Mars. Mandates significant reliability. Those words are doing enormous work. What they mean, translated from the careful language of academic publication, is that the return depends on systems that must work perfectly and that no one has yet proven can work at all. SpaceX promises a round trip. The marketing materials show starships launching from Mars, climbing through the thin Martian atmosphere, and returning triumphantly to Earth. The animations are beautiful. They show gleaming rockets and confident trajectories and a future that looks as clean and inevitable as a product launch video. But between those animations and reality lies the tyranny of the rocket equation. The unsolved problem of cryogenic boil-off, the untested challenge of ISRU at scale, and the unbroken chain of dependent systems that must each succeed for a single human being to make the journey home. The fuel to come home from Mars does not exist yet. The factory to make it has not been built. The technology to store it has not been proven. And the people who may one day board a starship bound for Mars deserve to know that the return ticket they were promised is, at this moment in history, a hope dressed in engineering language, not a guarantee, not a plan. A hope. And if the return does not materialize, if the ISRU plant fails, or the engines do not light, or the boil-off claims too much fuel, then the crew that landed on Mars with the expectation of coming home will discover that they are not visitors. They are residents permanently on a planet that was never meant to hold them. But even setting aside the physics, even assuming the technology eventually catches up and the return becomes possible, there is another set of questions about Mars colonization that have nothing to do with rockets or fuel. Questions about law, about power, about who decides what happens to the people who go. Because the legal framework that will govern life on Mars is being designed right now. Not by governments, not by democratic institutions, not by the people who will live under its rules, by a corporation. And the implications of that fact should concern everyone who has been paying attention. Buried in the terms of service for SpaceX's Starlink satellite internet, in a section most users scroll past without reading, there is a clause that should stop you cold. It reads, in part, that for services provided on Mars or in transit to Mars via Starship or other colonization spacecraft, the parties recognize Mars as a free planet and that no Earth-based government has authority or sovereignty over Martian activities. Disputes, it continues, will be settled through self-governing principles established in good faith at the time of Martian settlement. Read that again carefully. A private company incorporated in the United States, funded in part by billions of dollars in NASA contracts paid for by American taxpayers, has declared in a legal document that no government on Earth has authority over what happens on Mars. Not the United States government, not the United Nations, not any international body. This is not a joke. It is not an Easter egg. It is a legal assertion made by the company that is further along in the development of Mars transportation technology than any other entity on the planet. And it has been sitting in those terms of service since 2020, examined by legal scholars, challenged by space lawyers, and largely ignored by the general public. The Outer Space Treaty of 1967, signed by over 100 nations, including the United States, is the foundational document of international space law. Article 2 of that treaty states that outer space, including the Moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. Article 6 requires that states bear international responsibility for national activities in outer space, whether those activities are conducted by governmental agencies or by non-governmental entities. Article 8 provides that states retain jurisdiction and control over any registered space objects and any personnel thereof while in outer space or on a celestial body. In plain language, the treaty says three things. No country can own Mars, countries are responsible for what their companies do in space, and the laws of the launching country follow its citizens to whatever celestial body they travel to. SpaceX's terms of service contradict all three principles. Legal scholars have pointed out that Clause 9 should be regarded as void under international law because a private company cannot override the treaty obligations of its home country through a terms of service agreement. That is not how law works, but the more troubling question is not whether the clause is legally valid. It is what happens in practice. The Outer Space Treaty has no enforcement mechanism. There is no space police. There is no international court with jurisdiction over Martian activities. There is no practical way for any government to project authority across 55 million kilometers of vacuum. If SpaceX builds a colony on Mars and declares that colony to be self-governing, who exactly would stop them? What court would they answer to? What sheriff would serve the warrant? The gap between what the law says and what can be enforced is the gap in which everything dangerous lies. And it gets worse when you follow the money. Musk has suggested publicly that colonists could pay for their passage to Mars through loans. The cost of a ticket, he has speculated, might be around $100,000. A sum that most people would need to finance rather than pay outright. The loan would be repaid through employment on Mars, working for the colony, which in practice means working for the company that built the colony, transported the colonist, controls the life support, and owns every piece of infrastructure that keeps the colonist alive. Multiple legal scholars and ethicists have described this financial model in stark terms. A colonist who arrives on Mars in debt to the company that transported them, in a colony governed by that same company's self-described legal framework, on a planet from which they cannot leave and to which no external authority can extend meaningful legal protection, is a colonist with no leverage, no alternatives, and no exit. The historical parallels are uncomfortable and they are unavoidable. The company town where workers lived in company housing, bought goods at the company store, and were paid in company script was a feature of industrialization that democratic societies eventually outlawed because of the coercion inherent in the arrangement. Indentured servitude, where workers bound themselves to employers for a fixed period in exchange for passage to a new land, was a system that produced some of the most exploitative labor conditions in colonial history. The Mars colonization model, as currently described, shares structural features with both of these arrangements. The colonist depends on the company for transportation, shelter, oxygen, food, and governance. The company sets the terms. The colonist cannot leave if the terms become intolerable, and no external authority is positioned to intervene. What rights does a Mars colonist have? The right to quit? Quit and go where? The right to protest? Protest to whom? The right to leave? Leave on what spacecraft? The entire framework of labor rights, civil rights, and human rights that democratic societies have constructed over centuries depends on one fundamental assumption: that the individual has alternatives, that they can leave, that they can appeal to a higher authority, that they can, at the very last resort, walk away. On Mars, there is nowhere to walk to. The question of governance becomes even more complex if a colony grows. If it achieves something approaching self-sufficiency over decades, at what point do its inhabitants have the right to self-determination? A 2025 paper proposed treating Mars as a sovereign juridical peer to Earth, a political entity with its own legal standing, independent of the nations or companies that established the initial settlement. Legal scholars have examined whether Martian colonists could eventually constitute a people with rights to self-governance under international law. The answer is uncertain and deeply contested. International law does recognize the right of peoples to self-determination, but the definition of a people and the conditions under which that right can be exercised are among the most contentious questions in international jurisprudence. Would a few hundred colonists transplanted by a private company qualify? Would they need to reach a certain population threshold? Would they need to demonstrate political coherence? Would the company that established the colony voluntarily cede power? History offers no comforting precedents. Colonial powers have never voluntarily given up territory without struggle. Companies have never voluntarily surrendered authority over populations that they control. The path from colony to self-governing entity has, in virtually every historical case, passed through conflict. And the power asymmetry between a Mars colony and the Earth-based entity that supplies it with technology, replacement parts, and potentially new colonists would be unlike any power asymmetry in the history of human governance. The colony cannot survive without supply ships from Earth. The company controls the supply ships. The relationship is not between equals. It is between a population trapped in a sealed habitat on a lethal world and the entity that decides whether the next shipment arrives. There is something deeply strange about the fact that the governance framework for the first extraterrestrial human settlement is being drafted not in the halls of the United Nations, but in the terms of service of a satellite internet provider. That the political future of Mars is being shaped not by political philosophers or constitutional scholars or the people who will actually live there, but by a corporate legal team in Hawthorne, California. Is Mars colonization, as currently architected, freedom? Or is it the creation of a new kind of captivity dressed in the language of exploration? The answer to that question depends entirely on who gets to write the rules. And right now, the people who will live under those rules have not been consulted. They have not been asked. Many of them have not yet been born. The decisions being made today in boardrooms and legal departments and engineering meetings will determine the political reality of a world that no living human has ever touched. And those decisions are being made with remarkably little scrutiny, remarkably little public debate, and remarkably little concern for the historical patterns that should be flashing warning lights in every direction. But the legal questions, as urgent as they are, may not be the most important questions about Mars. Because while we debate who owns the planet and who governs the colony, science is telling us something that could make the entire colonization enterprise morally catastrophic. Something may already be living there, and we are about to step on it before we even know what it is. We talked about the Cheyava Falls rock at the beginning of this documentary, but that was the headline. Now we need the full story, because the full story is what turns Mars colonization from an engineering challenge into a moral crisis. In July of 2024, NASA's Perseverance rover was driving through Neretva Vallis, an ancient river valley on the western edge of Jezero crater. Jezero was chosen as the landing site for Perseverance specifically because orbital images revealed a river delta, clear evidence that a large lake once filled the crater billions of years ago. Lakes are potentially habitable environments. River deltas are excellent preservers of ancient life. If Mars ever hosted microbes, Jezero was one of the best places on the planet to look for their remains. The rover entered a region called the Bright Angel Formation, a set of rocky outcrops along the edges of the ancient river valley, and there it encountered a rock, arrowhead-shaped, roughly 1 meter by 0.6 meters. Unremarkable to look at first glance. The science team nicknamed it Cheyava Falls after one of the waterfalls in the Grand Canyon. Perseverance's instruments went to work. The PIXL instrument, which uses X-ray lithochemistry to map the elemental composition of rocks at the submillimeter scale, revealed something extraordinary. The rock was made of clay and silt, fine-grained sediment deposited by water. And within that sediment, arranged in patterns unlike anything the instrument had seen on Mars before, were concentrations of iron, phosphorus, and sulfur. Small dark spots, which the team called poppy seeds, dotted the surface. Larger formations, lighter in the center with dark rims, earned the name leopard spots. And the Sherlock instrument, designed specifically to detect organic compounds, confirmed the presence of organic carbon within the rock. On Earth, this combination of features tells a specific story. It tells the story of microbes, organisms that lived in mud, consumed organic matter, and in the process reduced iron and sulfur compounds, leaving behind distinctive chemical fingerprints in the minerals around them. The leopard spot pattern, in particular, is well known to geologists who study ancient microbial life on Earth. It forms when microorganisms create localized zones of chemical reduction in otherwise oxidized sediment. The reduced zones appear as lighter spots surrounded by darker iron-rich rims. The peer-reviewed paper, published in Nature in September of 2025, examined every plausible non-biological explanation for the patterns observed in Cheyava Falls. Could high-temperature processes have created them? The rock shows no evidence of having experienced the temperatures required. Could purely chemical reactions without biology have produced the mineral associations? The known abiotic mechanisms do not match the specific arrangement of iron phosphate and iron sulfide minerals found in the rock. The paper did not claim to have found life on Mars. Science does not work that way. What it said was that the textures, chemical characteristics, and organic signatures observed in the Bright Angel Formation warrant consideration as potential biosignatures. And the acting NASA administrator at the press conference announcing the findings said something more direct. He said that after a year of review, the scientists could not find another explanation, that this very well could be the clearest sign of life that we have ever found on Mars. Warrant consideration, clearest sign. These are the careful phrases that scientists use when they are standing at the edge of something enormous and do not want to fall in prematurely. But make no mistake about what they mean. They mean that we may be looking at the fossil record of organisms that lived in a Martian lake more than 3 billion years ago. They mean that life on Earth may not be unique, that the chemistry of living things may have ignited independently on two separate worlds in the same solar system. That would be the most significant scientific discovery in human history. More significant than the structure of DNA, more significant than the theory of relativity, more significant than the discovery of fire. Because it would answer the question that has haunted our species since we first looked up at the stars and wondered, are we alone? And then came the second study. In July of 2025, a team led by researchers at New York University Abu Dhabi published research in the International Journal of Astrobiology that introduced the concept of the radiolytic habitable zone. The key finding was this: galactic cosmic rays, the same radiation that threatens the health of astronauts, can penetrate the Martian surface and split apart water molecules in underground ice. When those molecules break apart, they release electrons and hydrogen. And on Earth, in the deep gold mines of South Africa, there is a bacterium called Desulfurodes audaxviator that survives by harvesting exactly this kind of radiation-driven chemistry. This organism lives kilometers below the surface in total darkness, completely cut off from the sun and from photosynthesis. It gets its energy from the chemical products of radiolysis. And the researchers showed through detailed simulations that Mars, with its thin atmosphere and subsurface ice, has environments where the same process could occur, not billions of years ago, right now. The energy available from cosmic ray-driven radiolysis in the upper few meters of the Martian subsurface is sufficient, according to the study, to sustain basic microbial metabolisms. The peak energy deposition occurs roughly 0.6 meters below the surface, close enough that human surface operations could easily disturb it. Close enough that a bulldozer preparing a habitat foundation or a drill extracting water ice could punch directly into the zone where life, if it exists, would be most concentrated. And this is where the two stories collide. On one hand, we have a potential biosignature in a Martian rock suggesting that life may have existed on Mars in the ancient past. On the other hand, we have a theoretical framework backed by simulations and by the existence of analogous organisms on Earth suggesting that life may still exist on Mars today, hidden just below the surface. And in between these two discoveries, there is a plan to land human beings on Mars and build a permanent colony. Human beings are biological disasters from the perspective of planetary protection. We are walking ecosystems. The average human body contains roughly 38 trillion human cells and roughly the same number of bacterial cells. We shed skin cells constantly. We exhale bacteria with every breath. Our gut microbiomes contain thousands of species of organisms, many of which are extraordinarily resilient. Some of these organisms can survive exposure to vacuum, extreme cold, radiation, and desiccation. They are, in many cases, harder to kill than we are. The planetary protection protocols maintained by COSPER, the Committee on Space Research, set strict standards for how much biological contamination a spacecraft can carry to Mars. Robotic missions are sterilized. Components are baked. Clean rooms are maintained. And even with these precautions, perfect sterility is never achieved. There are always surviving organisms tucked into crevices, embedded in adhesives, dormant in the most inaccessible parts of the spacecraft. For robotic missions, this residual contamination is a manageable risk. The chances that a few dormant bacteria on a rover will establish themselves in the Martian environment are considered small, though not zero. But human missions are a different category entirely. You cannot sterilize a human being. You cannot bake an astronaut in an oven to kill the organisms living on and inside them. The moment a human being sets foot on Mars, Earth life arrives in force. And once it arrives, it cannot be recalled. Every time an airlock opens, every time a suit is depressurized and brought inside, every time a colonist handles soil samples or drills into regolith or walks through an area where ice exists near the surface, there is a transfer of Earth organisms into the Martian environment. Over months and years, the contamination zone around a human settlement would expand. Earth bacteria would be introduced to Martian soil, Martian water ice, and Martian subsurface environments. If Martian life exists in the subsurface, and it is biochemically different from Earth life, we might be able to distinguish the two even after contamination. But if Martian life is similar to Earth life, if it uses the same basic chemistry, the same genetic molecules, the same metabolic pathways, then contamination could make it impossible to determine what was Martian and what was terrestrial. We would have destroyed the evidence before we knew what it said. And if Martian life is fragile, if it exists in small populations sustained by the thin energy budget of radiolysis, then the introduction of Earth organisms could overwhelm it. Earth bacteria are resilient, competitive, and adaptable. They have been shaped by billions of years of evolution in environments far more demanding than a Martian subsurface ice pocket. They could outcompete native organisms for the limited resources available. They could destroy a second genesis of life, proof that biology is not unique to our world, and we would never know what we had lost. Some of the most prominent advocates for Mars colonization have argued that even if Martian microbes exist, the moral imperative to preserve human civilization outweighs any obligation to preserve alien bacteria. They frame the question as a utilitarian calculation: billions of human lives against an alien microbe. The math, they say, is obvious. Others disagree profoundly. They argue that the discovery of a second independent origin of life would be the most important scientific finding in the history of our species. That it would tell us something fundamental about the probability of life in the universe. That it would reshape our understanding of biology, of chemistry, of our own origins. And that destroying it through carelessness or haste before we have even confirmed its existence would be an act of irreversible destruction that no moral calculus can justify. The ethics of this question are not abstract. They are operational. The Perseverance rover is on Mars right now with 30 samples collected and waiting for a return mission that has not yet been funded or fully designed. Those samples could contain the answer, but the samples sit on Mars in sealed tubes while the mission to bring them home remains in the concept phase, tangled in budget disputes and political indifference. We may be about to make an irreversible decision about another living world. And most of the people alive today have never been asked their opinion. The window to answer the question of whether Mars harbors life may close the moment settlement begins operation. And once that window closes, it does not reopen. Contamination is permanent. The question, unanswered, remains unanswered forever. That is the weight that the first boot print on Mars will carry. Not just the weight of a human being. The weight of a question that the entire species should have answered first. And yet, despite all of this, despite the radiation, the distance, the legal vacuum, the possible destruction of alien life, there are people who want to go, who have always wanted to go, who raised their hands when asked and said, "Yes, send me." Understanding who they are and why is essential to understanding what Mars colonization really means, not as an engineering project, but as a human one. In 2013, a small Dutch nonprofit called Mars One announced an open call for volunteers willing to make a one-way trip to Mars. The plan was straightforward in its audacity. Select a crew, train them, launch them, land them, and leave them there permanently. There was no return mission built into the architecture, no plan to bring anyone home. The entire concept was designed around the premise that the volunteers understood and accepted that they would live the rest of their lives on Mars and die there. 200,000 people applied from every continent, every age group, every walk of life. Teachers, engineers, doctors, artists, students, retirees, people with families and careers and houses full of things they would never see again. Not 200, not 2,000. 200,000 human beings looked at the prospect of permanent exile on a hostile world and said, yes. Mars One ultimately failed. The organization went bankrupt in 2019 without ever launching anything more than a feasibility study. The technology was never developed. The funding never materialized. The project was widely criticized as unrealistic, poorly planned, and in some assessments exploitative of the volunteers' willingness. But the volunteers were real. Their desire was real. And the sheer number of them demands an explanation that goes beyond dismissing them as dreamers or fools. Psychological studies of the most serious Mars One candidates revealed a consistent profile. High openness to experience, the personality trait associated with intellectual curiosity, creativity, and willingness to engage with the unfamiliar. High tolerance for ambiguity, the ability to function without clear answers or guaranteed outcomes, and elevated self-transcendence, the tendency to find meaning in purposes that extend beyond individual self-interest. To see oneself as part of something larger. To feel that contributing to a cause that outlives you is worth the cost of the contribution. These are not abnormal traits. They are not signs of pathology or recklessness. They are, in many ways, the traits that have driven every expansion in human history. The Polynesian navigators who crossed the Pacific in open canoes were open to experience. The first humans to migrate out of Africa were tolerant of ambiguity. The pilgrims who boarded leaking ships bound for a continent they had never seen were self-transcendent. The Mars One volunteers were not broken people seeking escape. Many of them had fulfilling lives, close relationships, professional accomplishments. They were not running from something. They were running towards something they could articulate in interview after interview with remarkable consistency. the chance to be part of the greatest adventure in human history, the chance to extend the reach of the species, the chance to stand on soil that no human being had ever touched and know that they were the beginning of something that might last forever. And yet, here is the hardest question this chapter has to ask. There is a difference between what the volunteers understood intellectually and what they could not have understood experientially. Humans routinely make commitments whose consequences they cannot fully anticipate. Marriage, parenthood, immigration, career changes. In all of these cases, the person making the decision has some abstract knowledge of what lies ahead, but cannot truly know what it will feel like to live inside that choice until they are already committed. The gap between knowledge and experience is always present. But for Mars colonization, that gap may be the largest in any decision a human being could make. The volunteer who applied at 29 imagined standing on red soil at dawn, the sun rising over the rim of a crater, the thin Martian sky shifting from black to deep blue to the salmon pink that Martian sunsets are famous for. They imagined exploration, discovery, purpose. They imagined the pride of being the first. They did not imagine, because they could not imagine, what it feels like to sit alone in a sealed habitat 5 years later watching a recorded video of their mother's funeral, knowing that the message they dread has been sitting in their inbox for 3 days because they were afraid to open it. They did not imagine the particular quality of silence in a room where the only sounds are the hum of the air recycler and the distant whir of a pump. They did not imagine what it means to look out a window and see nothing but dust and rock stretching to a horizon that never changes, knowing that this is the only view they will ever have for the rest of their life. Informed consent in medical and research ethics requires that a person understand not just the facts of a decision, but its material consequences. A surgeon must explain not just what will be removed, but what life will be like afterward. A researcher must describe not just the procedure, but the risks and the alternatives. Can informed consent be given for a life on Mars? The risks are quantifiable. Radiation doses can be calculated. Communication delays can be timed. Physical deterioration can be modeled. But the experience of living those risks day after day, year after year, with no possibility of reversal is something that cannot be modeled, can only be lived. And by the time it is lived, the consent that was given has already been irrevocably exercised. The volunteers of Mars 1 accepted a one-way trip. The current generation of volunteers, those who orbit the SpaceX community and who would board a Starship tomorrow if offered the chance, believe they are signing up for a round trip. SpaceX promises a return journey. The marketing materials depict starships lifting off from Mars and returning to Earth. But as we established earlier, that return depends on technology that does not yet fully exist. The ISRU plant has not been built. The cryogenic storage problem has not been solved. The reliability chain has not been tested. The volunteers of today may be signing up for something labeled round trip that functions in practice as one way. What obligations do mission architects have to make that distinction clear? At what point does optimistic framing become misrepresentation? If a volunteer consents to a Mars mission believing they have a 90% chance of returning, and the actual probability, accounting for untested systems and unsolved engineering challenges, is closer to 50%, has informed consent been obtained? These are not hypothetical legal questions. They are questions that will be asked in courtrooms or in congressional hearings if something goes wrong. If a crew arrives on Mars and discovers that the return is not possible, the consent forms they signed before departure will be examined under a legal microscope, and the question will be whether they were told the truth about what they were agreeing to. But beyond the legal questions, the existence of these volunteers tells us something about the human species that deserves to be taken seriously. Something in us responds to the call of the beyond. Something in us has always been willing to accept terrible risk in exchange for the chance to see what lies on the other side of the horizon. This impulse is not rational. It cannot be reduced to a cost-benefit analysis. It is deeper than reason. It is the thing that sent the first fishing boats out of sight of land, the thing that built the first ships capable of crossing oceans, the thing that put Neil Armstrong on the moon. The volunteers are not anomalies. They are what we are. The question is not whether the impulse is real. The question is whether it should always be indulged, whether the willingness to go is sufficient justification for being sent, whether the dream of Mars, beautiful and compelling and ancient as it is, should override the obligation to ensure that the dreamers understand what they are giving up. Because the price of going to Mars is not paid in money. It is paid in years, in relationships, in health, in the slow accumulation of losses that compound across a lifetime spent on a world that was not designed for human bodies or human minds. And the highest price may not be paid by the volunteers at all. It may be paid by people who never volunteered for anything, the children, the first human beings born on Mars who had no say in the matter and no option to leave. But before we reach the children, we need to talk about the technology itself. Not the dream of it. Not the animations and the promotional videos and the artist renderings of gleaming habitats on russet plains. The actual present-day, tested and untested technology that stands between the human species and a Mars colony. Because the gap between what has been demonstrated and what is required is not a gap that confidence alone can close. The largest object ever successfully landed on the surface of Mars is the Perseverance rover. It weighs approximately 1 metric ton, 1,000 kilograms, about the weight of a small car. Landing it required one of the most complex engineering sequences ever attempted. A heat shield absorbing the brutal deceleration of atmospheric entry, a supersonic parachute deploying at precisely the right altitude, a powered descent stage firing rockets to slow the vehicle further, and finally the sky crane, a hovering platform that lowered the rover on cables to the surface while the platform itself flew away and crashed at a safe distance. The entire sequence lasted 7 minutes. Engineers at the Jet Propulsion Laboratory called those 7 minutes the 7 minutes of terror, because there was nothing they could do but watch. The light speed delay meant the rover had already landed or already crashed by the time its signals reached Earth. A human Mars mission requires landing not 1 ton, but 50 to 100 tons, 50 to 100 times the mass of Perseverance. Habitats, life support systems, power generators, ISRU equipment, food, water, medical supplies, tools, and human beings who, unlike rovers, cannot survive a hard landing or be rebooted if something goes wrong. The physics of landing heavy payloads on Mars is fundamentally different from landing light ones, and the difference is not a matter of scaling up existing technology. It is a matter of inventing new technology that has never been demonstrated. The problem is the atmosphere. Mars has one, barely, and it creates a paradox for mission designers. It is thick enough to generate significant aerodynamic heating during entry, requiring a heat shield, but it is too thin to provide meaningful deceleration for heavy objects. A parachute that works beautifully for a 1-ton rover generates nowhere near enough drag to slow a 100-ton payload. The physics does not scale linearly. A parachute large enough to decelerate a Starship-class vehicle in the Martian atmosphere would be so enormous that the engineering challenges of deploying it become as difficult as the landing itself. SpaceX's proposed solution is supersonic retropropulsion, firing the vehicle's engines backward while the vehicle is still moving faster than the speed of sound through the Martian atmosphere. The engines push against the oncoming air, creating a complex interaction between the exhaust plume and the supersonic airflow that generates shock waves capable of destabilizing the vehicle. The company has demonstrated supersonic retropropulsion on Earth during Falcon 9 booster landings, but Earth's atmosphere is roughly 100 times denser than Mars's. The aerodynamic conditions are completely different. The shock interactions that occur when engines fire into a thin supersonic airstream on Mars have been described by engineers at the Jet Propulsion Laboratory as one of the hardest problems to model accurately. The shock fronts created by the engines interacting with the oncoming flow could potentially destabilize the vehicle during the most critical phase of landing. And there is no abort option. The vehicle either lands successfully or it does not. There is no going around for a second attempt. There is no runway to divert to. There is no ejection seat. The crew is inside a vehicle that is either performing a maneuver never before attempted at this scale on Mars, or they are inside a vehicle that is about to hit the Martian surface at a speed that turns everything inside it into debris. The engines themselves present their own challenge. A Starship arriving at Mars has been in space for 6 to 9 months. Its engines have been dormant for the entire transit, exposed to the radiation and temperature extremes of interplanetary space, subjected to the micrometeorite environment, and sitting idle with no possibility of maintenance or inspection. When the vehicle reaches Mars and begins its entry and landing sequence, those engines must ignite on command. First try. No test firing. No warm-up. The first time they light is the time they must work perfectly. If they do not ignite, the vehicle crashes. If they ignite but produce uneven thrust, the vehicle tumbles. If they ignite but cannot be throttled precisely enough to achieve a controlled landing, the vehicle impacts at a speed that no occupant survives. Every scenario except perfect execution ends in catastrophe. On the ground, assuming the landing succeeds, the technology must sustain human life indefinitely, And this is where the gap between what exists and what is required becomes most stark. The International Space Station uses what engineers call an open-loop life support architecture. Fresh supplies arrive regularly from Earth. Water, oxygen, food, and spare parts are delivered on resupply missions that dock every few months. The station does recycle some water and generate some oxygen from carbon dioxide, but these systems are supplemental. They reduce the amount of material that must be shipped from Earth, but they do not eliminate the need for resupply. If the supply ship stopped coming, the station would become uninhabitable within months. Mars colonies need closed-loop life support, systems that recycle water completely, that regenerate oxygen from carbon dioxide indefinitely, that process human waste into usable resources, that grow food using nothing but Martian soil, artificial light, and recycled nutrients. Systems that do all of this simultaneously without failure for years with no external resupply. No such system has ever supported humans for the multi-year durations Mars requires. The most ambitious attempt was Biosphere 2, a 3-acre enclosed ecosystem built in the Arizona desert in the early 1990s. 8 people entered the sealed facility with the goal of sustaining themselves for 2 years using only the resources inside. It did not go well. Within months, oxygen levels began to drop. The concrete of the structure was absorbing carbon dioxide and reacting with it, removing oxygen from the atmosphere faster than the plants could replace it. The crew experienced caloric restriction as food production fell short of projections. Interpersonal conflict escalated. Respiratory distress set in as the atmosphere degraded. Twice, additional oxygen had to be pumped in from outside, a correction that would have been impossible on Mars. Biosphere 2 operated on Earth in full gravity, with ambient temperatures that did not require heating, with abundant sunlight, with a team of engineers and scientists standing just outside the sealed doors ready to intervene if something went genuinely wrong. And it still failed to maintain stable life support for 2 years. Mars life support must outperform Biosphere 2 in every dimension. It must function in reduced gravity, which affects fluid dynamics and plant growth in ways that are not fully understood. It must operate without external support. It must handle the perchlorate-contaminated Martian dust that will inevitably enter the habitat. It must be reparable using only the tools and spare parts available on Mars. And it must do all of this without the option of opening the door because outside the door is death. And then there is medicine. On Earth, if you develop appendicitis, you go to a hospital. A surgeon who trained for years performs a procedure they have done hundreds of times in an operating room designed for the purpose, with anesthesiologists and nurses and sterile instruments and blood products and recovery wards. The surgery has a complication rate of less than 2%. It is routine. On Mars, appendicitis is a crisis. The surgeon may be a geologist who completed a 6-week emergency medical training module before departure. The operating room may be a table in the common area cleared of dinner trays. The instruments may be repurposed tools. The anesthesia may be managed by another non-specialist reading from a digital manual on a 20-minute delay from a consulting physician on Earth whose advice arrives after the critical decision has already been made. An appendicitis is a relatively simple condition. What about a stroke, a heart attack, cancer, which radiation exposure makes significantly more likely? A complex fracture requiring surgical stabilization, a dental abscess that progresses to a systemic infection. Each of these conditions requires specialized knowledge, specialized equipment, and on Earth, a specialist who devoted their career to treating it. A Mars crew cannot include a specialist for every possible condition. The crew is small. Every member has multiple roles. The person performing emergency surgery may be the same person who was fixing the water recycler that morning. Even dental care, something we take for granted as a minor medical concern, becomes a potential life-threatening emergency on Mars. An untreated tooth abscess can progress to a systemic infection within days. The antibiotics to treat it must have been anticipated, packed, transported across 225 million kilometers, and stored without degradation. If the right antibiotic is not available, if the abscess does not respond to treatment, the infection can spread to the bloodstream. On Earth, you go to the emergency room. On Mars, you manage with what you have or you die. The gap between what medicine can do on Earth and what it can do on Mars is the distance between life and death, measured in the weight of a dental kit that someone had to decide years before launch whether to include. The technology to go to Mars exists or nearly does. The technology to land on Mars, to sustain life there, to return from there, to practice medicine there, to grow food there, to survive there for years or decades, does not exist in the form that would be required. Pieces of it have been demonstrated. Proofs of concept have been achieved. But the integrated system, the complete end-to-end chain of technologies that must all work simultaneously for a human colony to survive, has never been built, never been tested, and never been operated at the scale and duration that Mars demands. We are not going to Mars with proven technology. We are going to Mars with a plan to develop the technology along the way. And the people inside that plan, the human beings whose lives depend on every link in the chain, deserve to know the difference. And they deserve to know something else, too. Something that no amount of engineering can prevent. People will die on Mars, not as a possibility, as a certainty. The only question is when and how, and whether we are honest enough to say so before we send them. This chapter is quiet. It has to be, because what we are discussing now is not engineering or politics or orbital mechanics. It is the certainty that human beings will die on Mars, not as a risk to be calculated, not as a probability to be managed, but as an inevitability to be faced. Every Mars mission architecture, every plan ever drafted by NASA or SpaceX or the European Space Agency or any private organization that has seriously examined the problem, includes a fatality probability that would be considered unacceptable in any other context on Earth. NASA's own radiation studies estimate that the excess cancer mortality risk for a Mars round-trip crew could exceed 5% at the central estimate. The upper bound approaches 10%. That means 1 in 10 crew members may die of radiation-induced cancer as a direct result of the mission. 10%. A commercial airline with a 10% fatality rate would be grounded permanently. A hospital with a 10% surgical mortality rate would be shut down and investigated. An industrial operation with a 10% worker fatality rate would be closed by regulators and its operators prosecuted. And that is radiation alone. It does not include the probability of landing failure, of life support malfunction, of habitat breach, of medical emergency, of the 100 other ways that Mars can kill the people who attempt to live there. Each risk adds to the cumulative probability. And when you compound those probabilities across a multi-year mission involving a small crew with no possibility of rescue, the likelihood that the first crewed Mars mission produces at least one death is not small. Mission planners know this. Engineers know this. The people who design these missions have calculated the probabilities and incorporated them into their planning. They call it acceptable risk. They define thresholds. They draw lines on graphs and assign numbers to outcomes. And in the quiet mathematics of risk assessment, a 5 or 10% chance of losing a crew member is considered tolerable because the alternative, never going at all, is considered worse. But someone should say it plainly, because the people who will board those spacecraft deserve plain language, not probability distributions. People will die on Mars, specific people with names and faces and families who will miss them. And the deaths will not be heroic abstractions. They will be concrete events involving fear and pain and the particular aloneness of dying on a world where help cannot arrive. Think about what it would actually mean. A crew member dies on Mars. Perhaps a suit breach during a surface excursion. The depressurization is rapid. The cold hits first, then the vacuum. The other crew members watch it happen from 10 meters away, unable to reach their colleague before the atmosphere inside the suit is gone. They recover the body. They carry it inside. And then they are standing in a habitat that was designed for 6 people but now holds 5, looking at someone they lived with for over a year, someone they ate meals with and ran diagnostics with and argued with about nothing. And that person is dead. There is no hospital to take the body to. There is no mortician. There is no funeral home. There is no protocol yet for what you do with a human body on the surface of Mars. Do you bury it? The Martian regolith is cold and dry and laden with perchlorates. Do you preserve it in the hope that a future return mission might bring it home? That requires resources, refrigeration, space in a habitat that cannot afford to waste any. Do you cremate it? That requires energy that the colony may not be able to spare. The surviving crew notifies Earth. They record a message. They describe what happened. The message travels at the speed of light and arrives on Earth between 4 and 24 minutes later. The family learns that their loved one is dead. They learn this fact from a recording, not from a person. They cannot ask questions. They cannot say goodbye. They cannot hold anyone who was there when it happened. And the surviving crew must continue working. The mission does not stop because someone died. The life support still needs maintenance. The ISRU plant still needs monitoring. The habitat still needs to function. The crew, now smaller, now traumatized, now carrying a grief that has no outlet and no ritual to contain it, must perform the same tasks with fewer people, each of them knowing, in a way that they could not have fully known before, that the same thing could happen to them tomorrow. The death of the first human being on Mars will be the most watched death in human history, not in real time because the light speed delay prevents that, but in the hours and days that follow, when the recordings and the reports reach Earth, the entire world will witness what happened. And the death will have occurred, from Earth's perspective, many minutes before anyone on Earth knew it was happening. There is something particularly cruel about that delay. The moment of death exists in a kind of temporal solitude. It happens on Mars, observed only by those present, and does not become real to the rest of humanity until the light carrying the news finishes its long journey through the void. But the first death on Mars, as devastating as it would be, is not the heaviest thing this chapter has to carry. The heaviest thing is the children. We talked about them earlier, the biology, the bones that form in reduced gravity, the bodies calibrated for a world that is not Earth. We talked about them in the radiation chapter. The developing cells, the risks that no one has quantified because no one has been willing to run the experiment. But we have not talked about what it means emotionally for a child to be born on Mars. A child born on Mars did not choose to be there. That sentence is worth sitting with. Every ethical framework we have for discussing risk and consent begins with the premise that the person exposed to the risk had the opportunity to agree or refuse. Adults who volunteer for Mars can give informed consent, however imperfect. Children born on Mars cannot give consent at all. Their existence on that world is a consequence of their parents' decision. A decision made for them without them before they existed. That child will grow up in a sealed habitat. The largest room they will ever know will be measured in meters, not kilometers. They will not walk through a forest. They will not feel rain on their skin. They will not wade into an ocean or climb a mountain or sit in a field of grass under an open sky. Everything they know about Earth, about the world their species evolved on over millions of years, will come from screens and stories and the fading memories of adults who once lived there. They will know they are human, but they will experience almost nothing of what humanity, as a civilization, has accumulated over thousands of years. No concerts, no crowds, no cities, no neighborhoods where you can walk to a friend's house, no natural landscape that does not require a pressure suit to visit. Their world will be small and engineered and utterly dependent on technology for every breath. And if the biology we discussed is correct, if their bodies calibrate to Martian gravity during development, they may never be able to visit Earth, the world their parents left, the world that every story and every lesson and every recorded message from across the void tells them is home, will be a place they can see but never touch, a dot of light in the Martian sky impossibly far away, containing everything their species has ever built and inaccessible to them, as if it were in another galaxy. The first child born on Mars will be the loneliest human being in history, and they will have no idea why, because loneliness for them will not be a condition, it will be the world. It will be all they have ever known. They will not miss Earth because they have never been there. They will not grieve for what they lost because they never had it. They will simply live in a small habitat on a cold world under a sky that does not protect them, surrounded by adults who remember something better and cannot explain, not really what it felt like. The parents chose Mars. The children inherited it. And the gap between choosing a world and being born into it is a gap that no amount of engineering or enthusiasm can close. When we talk about Mars colonization, we talk about rockets and habitats and fuel and technology. We talk about it as an engineering problem with engineering solutions. But the first Martian graves will not be an engineering problem. They will be a human one, bodies that failed, minds that broke, lives that ended far from everything that once gave them meaning. And somewhere in that colony, a child looking at a pale blue dot in the sky, not knowing what it means, not feeling the loss, because they never had the thing that was lost. That is the true price of going to Mars. Not the money, not the fuel, not the technology. The price is measured in human lives that will be shorter, harder, more isolated, and more constrained than any lives humans have lived since we first walked out of Africa and spread across a planet that, for all its dangers, at least had air we could breathe and water we could drink and a sky that did not want to kill us. And the question that hangs over all of it, the question that this entire documentary has been building toward, is whether the price is worth paying. Let us be honest about what is lost, not abstractly, specifically, because the losses of Mars colonization are not theoretical. They are concrete and they accumulate across a lifetime. A parent watches their child's first steps in a recorded video that arrives 3 weeks after the steps were taken, By the time they see it, their child is already running. The moment is already gone. They record a message of joy and send it back, and it arrives on Earth 3 weeks later, when the child has moved on to something else entirely. The parent and the child exist in the same universe, but not in the same time. A spouse grows old on a different planet. The messages continue for years. They share news. They describe their days. They say, "I love you" into a camera and send it into the void. But the spontaneity that makes love feel alive, the unexpected touch, the shared silence in the same room, the ability to turn to someone in the middle of the night and know they are there, all of that is gone. What remains is correspondence. Beautiful perhaps, devoted perhaps, but not presence, never presence again. A friendship sustained for years through asynchronous messages eventually goes quiet. Not because anyone stopped caring, because correspondence is not the same as companionship. Because the effort of maintaining a connection across a 20-minute time delay and a widening experiential gap becomes heavier with each passing year, and eventually silence is easier. Not better, easier. Cultural belonging disappears. The colonist receives news of political events in countries they no longer inhabit, cultural movements that evolved without them, music they have never heard performed live, jokes whose references they no longer share. The language itself may drift. Slang changes. New words enter common usage. The colonist speaks a version of their native language that is gradually becoming archaic, while the living language on Earth moves on without them. The Earth the colonist left behind becomes, over years, a foreign country, a place they remember but no longer recognize, a place where they would be a stranger if they could somehow return. And they know this. They watch it happen in the messages and news broadcasts and cultural artifacts that arrive from a world moving forward without them. They become a historical figure while they are still alive, occasionally remembered, rarely considered, the subject of a documentary watched by people who will never meet them. And their body, bone by bone and cell by cell, it is becoming something that cannot go back. The skeleton thinning, the heart remodeling, the radiation accumulating in every tissue, the eyes changing, the lifespan shortening. Not dramatically, not all at once, but steadily, measurably, irreversibly. The colonist is becoming Martian in the most literal sense. Their biology is being shaped by a world that is not the world their genes were written for. This is what is given up. Not in a moment of dramatic sacrifice, but in a slow accretion of small losses that compound across years until the person who left Earth is no longer, in any biological or cultural or experiential sense, the same person who arrived on Mars. Now, let us be equally honest about what might be gained. Because dismissing the case for Mars colonization is not honest either. And the people who want to go deserve to have their reasons taken seriously. The insurance argument is the strongest and the simplest. The human species currently exists on one planet. Every person, every culture, every book, every piece of music, every memory, every achievement in the entire history of human civilization exists on a single rock orbiting a single star. If something happens to that rock, if an asteroid strikes, if a pandemic escapes containment, if nuclear war destroys the infrastructure that keeps 8 billion people alive, then everything is lost. Not just us, everything we have ever made or thought or loved or wondered about, gone. A self-sustaining colony on Mars would be an insurance policy against that extinction. Not a comfortable one, not a luxurious backup, but a continuation. A remnant of the species that would carry forward the accumulated knowledge and culture of a civilization, however imperfectly, into a future that Earth's destruction would otherwise have erased. Is that worth the cost? The cost we have spent 12 chapters documenting. The broken bones and damaged brains and stranded families and lonely children. If the alternative is the total extinction of everything human, then maybe the suffering of thousands is justified by the survival of the species. Maybe the children born on Mars, who will never see Earth, are a price that the 8 billion people on Earth are willing to pay on their behalf. The meaning argument is harder to quantify, but equally real. Some lives can only be fulfilled through extraordinary challenge. The Mars One volunteers were not deluded. Many of them understood the risks with remarkable clarity and chose to go anyway. They found meaning in the purpose itself, in being the first, in contributing to something that would outlast their individual lives. This is not pathology. This is a deeply human response to the fundamental problem of mortality. We all die. The question is whether what we did before dying mattered. For some people, The only satisfactory answer to that question involves reaching for something that most people would consider impossible. The expansion argument draws on the full sweep of human history. Every frontier has required people willing to pay prices that their stay-at-home contemporaries considered absurd. The first Polynesians to navigate to Hawaii left behind everything they knew and set out across open ocean in canoes with no guarantee of finding land. Thousands of them died. The ones who survived established one of the most remarkable cultures in human history. The first European colonists to cross the Atlantic endured mortality rates that would horrify a modern ethicist. Half the Mayflower passengers died in the first winter. And yet, 3 centuries later, the civilization that grew from those desperate suffering colonies had become the most powerful on Earth. Were those deaths justified? That question cannot be answered without imposing one moral framework over another. The dead cannot weigh in. The descendants who benefited from the sacrifice have an obvious bias. The contemporaries who stayed behind were proven wrong in their pessimism, but they were not irrational at the time. Mars colonization fits this pattern. The people who go will suffer. Some of them will die. The civilization they build, if they build one, will take centuries to develop. And the people alive today who are making the decision to go or not to go are doing so with radically incomplete information about what the future holds. Perhaps the volunteers for Mars are right about something we cannot yet see. Perhaps the act of reaching for another world, despite the cost, despite the suffering, despite the uncertainty, will prove to be the most important thing our species ever did. Or perhaps it will prove to be a tragic miscalculation, a project born of hubris that consumed lives and resources that could have been better spent solving the problems of the world we already have. We do not know. We cannot know. And the honesty of admitting that is more valuable than any confident prediction in either direction. But there is one more dimension to this question, one that lifts it out of the domain of individual choice and into the domain of collective decision. Mars colonization is not just a decision individual volunteers make. It is a decision the human species is making about what kind of thing it wants to be. A species that stays home, that tends its garden, that solves its existing problems before reaching for new ones. Or a species that expands, that accepts tremendous individual sacrifice in exchange for the possibility of long-term survival and growth, that is willing to let some of its members become permanently other in order to ensure that the whole does not perish on a single world. This is a political and philosophical question dressed in engineering language, and the public has never been asked to vote on it. The decision is being made by companies and space agencies, by engineers and executives, by people who will not personally bear the costs of the decision they are making. The volunteers who raise their hands will pay the price. The children who are born on Mars will inherit the price. But the decision itself, the decision to commit the first Martians to permanent exile on behalf of all the rest of us who get to stay, that decision is being made without the consent of most of the people it affects. Who decides? That is the question this documentary has been circling since the first chapter. Who was elected? Who was authorized? Who looked at all the evidence, all the risks, all the costs and said, yes, this is worth it? Because if we are going to send human beings to die on another world, if we are going to create a new branch of the human species that can never come home, if we are going to risk contaminating an alien biosphere before we know what lives there, then the decision should be made in the open. By everyone. Not in a boardroom, not in a terms of service agreement, not in an animation rendered by a marketing department, in the open, where the costs are named, where the losses are counted, where the price is visible. And that brings us, finally, to the end, to the pale blue dot, to the moment that everything we have discussed becomes real. Picture the moment. A human being stands on the surface of Mars. They are suited, helmeted, breathing recycled air that tastes faintly of the filters that cleaned it. Their boots press into regolith that no human foot has ever touched before. The ground beneath them is iron oxide, rust, the color of old blood, stretching in every direction to a horizon that is slightly closer than Earth's because Mars is a smaller world. It is early morning. The sun is rising, smaller than it appears from Earth, casting a light that is noticeably dimmer, noticeably colder, noticeably less like home. The sky is not blue. It is a pale butterscotch, thinning to something like lavender near the horizon where the fine dust particles in the atmosphere scatter what little light they can catch. The astronaut looks up, past the sun, past the thin sky, into the darkness above, where stars are visible even during the Martian day because the atmosphere is too thin to wash them out. And somewhere in that darkness, low on the horizon, barely distinguishable from the surrounding points of light, there is a faint blue dot, Earth. That dot contains 8 billion people. Every book ever written, every piece of music ever composed, every act of love or cruelty or genius or ordinary kindness in the history of human civilization. Every person the astronaut has ever known, every street they have ever walked, every room they have ever slept in, every conversation they have ever had that lasted past midnight because neither person wanted it to end, all of it compressed into a point of light. They will never get closer to it. That fact settles into the astronaut like a physical weight. They have known it intellectually since before they launched. They signed papers acknowledging it. They discussed it with psychologists. They told their families. But knowing it and feeling it are different things. And right now, standing on the surface of a world that is trying to kill them in every way a world can try, looking at the pale blue dot that contains everything they have ever loved, they feel it. In 1990, the Voyager 1 spacecraft, at the urging of astronomer Carl Sagan, turned its camera back toward the inner solar system from a distance of 6 billion kilometers. The photograph it captured showed Earth as a speck of light, a fraction of a pixel, suspended in a scattered beam of sunlight. Sagan called it the pale blue dot, and his words about that image have become some of the most quoted in the history of science. He spoke about the smallness of Earth, about the folly of human pretensions, about the responsibility to deal more kindly with one another and preserve the only home we have ever known. The astronaut on Mars is seeing something Sagan never saw, not a photograph, the real thing. From a distance of 55 million kilometers on a good day, 200 million on a typical day, the Earth is not a world. It is a point of light. And everything the astronaut has given up, everything they will never experience again, is contained in that point. This documentary does not take a position on whether Mars colonization should happen. That is not its place. The question is too large, too consequential, and too personal for any single film to answer. What it can do, what it has tried to do, is lay out the costs as plainly as possible so that the decision, when it is made with open eyes. But this documentary does take a very clear position on one thing: what those who stay behind owe those who go. They are owed the truth, not marketing, not inspiration dressed as information, not animated videos showing gleaming rockets and clean habitats and confident timelines. The truth, the full, unvarnished, uncomfortable truth about what is known, what is unknown, and what is being assumed. They are owed transparency about risk, not probability distributions buried in technical papers, but clear-eyed acknowledgement in plain language of what the mission planners believe the actual chances of survival are, and what the chances of return are, and what the difference is between those two numbers and the numbers the public has been given. They are owed the best technology that can be developed before they depart. Not next year's technology, not the version that will be ready in a decade, but the technology that exists and has been tested at the time of launch. Whatever possibility of return can be kept open should be kept open. Whatever risk can be reduced should be reduced. Whatever uncertainty can be resolved before departure should be resolved, not deferred. And they are owed something that costs nothing, but that may be the hardest thing of all to provide. They are owed the promise that they will not be forgotten. Not as abstract pioneers, not as names on a plaque, not as characters in a story told to inspire the next generation. As specific human beings with names, with families, with fears they never told anyone, with moments of doubt at 3 in the morning when the habitat was quiet and the pale blue dot was just barely visible through the porthole, with losses they accumulated one by one across years of exile, with laughter that echoed off metal walls, with love that survived the 20-minute delay, with grief that no ritual could contain. The first Martians deserve to be remembered as people, not as symbols, not as martyrs, not as data points in a mission report, as human beings who agreed to pay a price that most of us will never pay for a future that most of us will never see. And now we arrive at the question that has been waiting since the beginning. The question that has no answer and should not have one because resolution would be false. Is this worth it? Return to the Cheyava Falls rock, that leopard-spotted stone in Jezero crater holding what may be the fingerprint of ancient Martian life, the most important scientific sample in human history sitting in a sealed tube on the surface of Mars waiting for a return mission that has not been funded. We may be about to contaminate a world that holds the answer to our deepest question before we have had the courage to bring the sample home and look. Return to the delay. February 9, 2026. The Mars mission shelved. The 2026 window closed. The timeline slipping again, not because the dream is fading, but because the physics is stubborn and the engineering is hard and the gap between ambition and reality keeps refusing to close. Every version of the future arrives later than promised. Return to the volunteers, hundreds of thousands of them, hands raised, willing, knowing the risks, at least in the abstract, and saying yes anyway. Because something in the human spirit responds to the beyond. Because something in us has always needed to know what lies on the other side. Because staying safe has never been the thing that defined us. Return to the children. The ones who will be born on Mars if a colony survives long enough. The ones who will develop in 38% gravity under a radiation flux we have never tested on a developing human body, inside a habitat they did not choose on a world they cannot leave. The ones who will look at the pale blue dot and know that it is home in some ancestral sense without ever understanding what that word means in the way their parents understood it. We are, for the first time in the history of our species, seriously planning to send human beings to live and die permanently on another world. The technology is not ready. The ethics have not been resolved. The governance has not been established. The science that might change everything about what we think we know about Mars has not been completed. And yet the planning continues. The rockets are being built. The volunteers are waiting. The window is always opening and closing. What we think about this matters. What we feel about it matters, not because our feelings will change the physics, but because the decisions being made right now in this decade will determine whether human beings live or die on another planet within our lifetimes. And those decisions are being made right now by a very small number of people for a very large number of people with very little public conversation about what is actually at stake. The question is not whether humans will go to Mars. Eventually, we probably will. The question is whether we go with our eyes open, whether we go honestly, whether we name the costs before we pay them, whether we remember the people we send as people, not as missions, whether we look at the pale blue dot from both directions, from Earth looking out and from Mars looking back, and understand that the space between those two points of view contains everything that makes us human. The distance, the silence, the irreversibility, the loss, and the stubborn, irrational, magnificent refusal to stop reaching. Somewhere tonight on Earth, someone is looking up at the sky. They can see Mars, a faint red point among the stars, and they are thinking about going there. They are imagining what it would feel like to stand on that world and look back. They do not fully understand what it would cost them. Nobody can until they are standing there. But they want to go anyway. And somewhere in the future, if we do this thing, if we send them, a human being will stand on Mars and look up at the pale blue dot. And they will understand, in a way that no one on Earth can understand, what it means to be far from home, what it means to have given up everything that the word home contains, what it means to belong to the distance. Two worlds, 2 points of light, the same darkness between them. And the question, still unanswered, still worth asking. Is it worth it? You are still listening. You are still here on this world under a sky that protects you, breathing air that asks nothing in return. The pale blue dot is not above you. It is beneath you. You are standing on it. Hold on to that. Not everyone will have the choice. Thanks for watching this deep and sobering exploration of what it truly means to go to Mars. If you enjoyed this video, please give it a like and subscribe to the channel for more in-depth documentaries that challenge how you see the world. Share your thoughts in the comments below. Do you think we should go to Mars? Or should we wait until we fully understand the costs? And don't forget to hit that notification bell so you never miss an upload. Until next time, keep questioning, keep wondering, and never stop looking up.